Hi everyone, I'm Samir and I'm one of the team leaders in this workshop, and we'll mostly be working on audio generative modeling. Is this fine? Okay. We'll mostly be working on building an audio generative model that can basically generate audio conditioned on different prompts, so our main goal is like to build like a universal audio generator. So in this talk, about my background, I am currently working in Mitsubishi Electric Research Lab in Cambridge, Massachusetts. And last year, I was a PhD student at MIT. I think there will be some PhD students here as well. Um, I'll basically talk about some basic ideas that go into building audio generative model or generative models in general. So you must have seen like a lot of papers on generative modeling, generative AI, right? I think I'll try to focus on basic key ideas, and all these papers are some modification of those key ideas. Um, so some ideas like autoencoders, and you must have seen like masked autoencoders, right? And masked prediction is like a key idea in self-supervised learning for audio. Uh, the other key idea is like vector quantization. So compressing like high dimensional image or audio data into like low dimensional codes and then building a generative model on top of that is like pretty common. In most recent papers, you'll see that thing happening. And there are some like new ways of doing vector quantization. I'll talk about those as well. Variational autoencoders is an old idea again, but now it is used in conjunction with like diffusion models, right? So with diffusion models, you model the latent space of the VAE. So I think it's good to know that basic idea as well. I won't talk about some things like which are popular these days, like diffusion, for example. I think maybe you have heard about diffusion in your some previous talk. So that's good, but I won't touch on that, unfortunately. I'll mostly be talking about like generative modeling. So again, another key idea is like future prediction, right? Generative pre-training is just that. Uh, those ideas are also used in audio generative modeling. So I'll go through some math behind those ideas and try to convey the overall picture. So my talk will focus on compression of high dimensional data. That would be the main focus of the talk. And compression is mostly focused on like learning low dimensional codes given some high dimensional data. So the goal in compression is generally faithful reconstruction or generation. So you should be able to reconstruct or generate from those compressed codes your high dimensional data faithfully. Some seminal works in this area are variational autoencoders, vector quantization, variational autoencoders, VQ-GAN, and residual vector quantization VAEs. So I'll talk about these things in more detail. Um, so neural vector quantization is often used as a first step in audio generative modeling. So I mean, if you think about how you build generative models, you can think about generative pre-training like GPT models, right? But if you try to build GPT on audio, which is very high dimensional data, you would not be very successful. So generally, the key idea is to compress audio into some low dimensional codes, which has the same sampling rate. I think there's a better term for that. Maybe the same length as text tokens, and then you can do generative pre-training on that. Some seminal works of generative modeling on these compressed codes is AudioLM from Google and MusicGen from Meta. So I'll talk a little bit about these ideas as well. And these are very recent papers, actually. And VAEs, as I said, are used as first step of diffusion models, and seminal work for audio generative modeling here is Audio LDM, which is also like last year they came out with Audio LDM 2. So all pretty state-of-the-art methods. I'll also talk about self-supervised learning for audio. Here, the goal is slightly different. The goal is not faithful generation of audio, but learning some abstract representations of audio. If you're familiar with speech, there are these latent structures in speech like phoneme categories, words, and grammar, syntax, etc. So these self-supervised learning methods try to encode some of those structures. So more, I would say, like structural features of the speech signal. And these compression algorithms are mostly focusing on learning like low-level fine-grained details of the audio. So actually, these two things together are used for building generative models. If you only build your generative model using fine-grained tokens from the vector quantization, you will not get very good generation. Like the structure will be all messed up. So here some seminal works are contrastive predictive coding, which is a old, like not old, but 2018, the paper came out, and that led to a series of self-supervised learning methods like Wave2Vec, 2.0, Hubert, all from Meta and BestRQ from Google. Audio MAE beats are not speech-specific models, but they used this idea of masked autoencoders for modeling general sounds. So I'll talk about like those ideas as well. I don't know if I'll be able to cover all of them, but like that's in my slide. So let's see how far we can go. You might have heard about CLIP, also like contrastive language image. There's also contrastive language audio pre-training. Uh, but yeah, I think I won't focus on that. So as I said, like compression and self-supervised learning have some similarities. Like they both aim at uncovering some latent structure, but they aim at uncovering different types of latent structures. And yeah, I think I covered the differences a little bit. Okay, so let me start with some like basic ideas about compression. Like how do you go about compressing high dimensional data? So autoencoders is one old idea. So in autoencoders, so yeah, I think let me go to the board now. So let's start with the autoencoders, right? So autoencoders is a pretty simple idea. You have some high dimensional vector. Let's say it's a d-dimensional vector. You compress it into some latent code using some encoder. And then you have this Z. Z is generally t-dimensional, right? There's a decoder that tries to reconstruct this high-dimensional data back. So let's call it X hat. And that's also d-dimensional, right? Generally, P is smaller, much smaller, I would say, than D. The goal in autoencoder, I think you are familiar with it, is to minimize the reconstruction loss. So how you train these functions, encoder and decoder, is by minimizing reconstruction between the input and the reconstructed output from the decoder. So, we can write this simply as this. This is generally the loss function. Parameters are the parameters of the encoder and the decoder. So that's a simple autoencoder, right? The P here doesn't have to be low dimensional. So for example, in masked autoencoders, P is generally not low dimensional. It has the same dimensionality as the data. In masked autoencoders, so I have some slides on that. So yeah, in autoencoders, you can also have some regularization on Z. So you can make a Z sparse or Gaussian, for example, by adding some noise to it. That can be useful for some downstream applications. So this Z thing here is also called the bottleneck, and it learns some low-dimensional latent code. And the encoder and decoder are generally neural networks in autoencoders. So what is it used for? Like dimensionality reduction is an application of autoencoders. So if like the P here is 2, then you can like plot the latent space into and visualize your data, right? There's some structure, maybe some clustering structure in your data. Classification, you can use this latent code for some downstream application, and you can train your classifier with a few labels, right? Because this is much low dimensional, your classifier would require less parameters. So you can do like few short learning with this latent code. Yeah, sure.
Notation.
Yeah.
You wrote X is in RD and X hat is in RD.
Yes.
And B is in RP where P is less than D.
Yeah.
Are we going to stick to this, or are we going to let's also allow later RD cross N where X
Yeah, definitely. I think, yeah, for sure.
Okay, so I don't have to think about D as the length times dimension.
No.
It's just dimension for now, and then we can.
Yeah. Okay. So yeah, go ahead. Yeah. Yes. It means the same thing, yes. So it's a continuous representation that you're learning, but it's much low dimensional. So, as Sanjeev pointed out, like it doesn't have to be these vectors. These are like generally tensors, right? So if you're modeling an image, for example, an image would have X, for example, H, W, and 3. So it's a RGB image, let's say. So your latent code would be something like H by whatever downsampling factor you want, H by 4, across W by 4 and some channels, So this can be, so this is generally like a representation which is much low dimensional than your data. And it tries to remove noise from your data. Like it tries to get at some latent structure that you believe exists in your data. So for images, the latent structure would be objects, right? Um, so if you're modeling faces, then it would be nose, ears, and those type of high-level features. For speech, this latent code would be phoneme categories, for example. Or if it's like a really abstract latent code, it could also encode like a word information, for word segmentation, things like that. So that's what the latent code is getting at this high-level structure. And then you can use this latent code for some downstream application to have some efficient training. So this is an old example from Hinton et al. Of autoencoder doing dimensionality reduction on these faces. So this is like a common structure for autoencoder. You have some neural network that goes from some high dimension and gradually downsampling to some latent code. So here the latent code has only 30 units. So it's a 30-dimensional vector, right? And then the decoder is generally the transpose of the encoder. That's a very common structure that is used in like all modern like autoencoders or VQVAEs. I'll show some examples of like very recent work. So here, yeah, I think I covered this. So in this paper, they showed that like with autoencoder, you can get much better reconstructions compared to like PCA. So I mean, it wasn't obvious in 2006, I guess, but now I think that if you model your data with an autoencoder with neural networks, you'll get better reconstructions. So also they showed with digits and also with faces. The second row here is the autoencoder and the last row is the PCA. So I think in 2006 it was PCA was the most dominant like dimensionality reduction technique, and they showed that with autoencoders, neural networks, you can get much better results. Also, so as I said, like the latent code is aiming at some high-level structure in your data, right? So if you are building your autoencoder on, so are you guys familiar with this data set called MNIST, with handwritten digits, right? So here, like 0 to 9 are the labels of the digits, right? And basically how they get this visualization is by passing the MNIST test set through the encoder of the autoencoder and then plot those latent codes in this space, right? Labeled by the digits. So here you see like the PCA has no high-level structure that you can see. But the autoencoder latent space has this clustering structure, right? Like the codes are clustered according to the digit labels, right? So that's the kind of structure that I'm talking about, that the autoencoder or these dimensionality reduction methods are trying to get at. Also, like if you train the autoencoder on documents like text, you also get this kind of clustering structure according to topics. So the topic is the high-level latent structure in the documents, right? But the PCA is not able to recover that. And that's because of obviously the neural networks. So now so this was the, just a brief summary of autoencoders. I think people do use autoencoders still, but they use denoising autoencoders. And you must have heard about masked autoencoders from Florian. That's a denoising autoencoder. So denoising autoencoder, here the latent codes are actually high dimensional. So instead of doing dimensionality reduction, you are learning a code that is higher dimensional than your input vector. What that does is it can do something like this. So it can, in a higher dimension, your data can be linearly separable. So this visualization I found on YouTube actually shows that in 2 dimensions, the data is not linearly separable. So the blue dots and the red dots are not linearly separable. So you cannot divide these two things with a straight line, right? Like the decision boundary here is, for example, a circle. But if you embed this data into 3 dimensions, then it can become linearly separable. So let's look at this one. This is actually the idea behind denoising autoencoder. It does not do dimensionality reduction, it learns a higher dimensional representation. So I think they are showing like with SVM, with kernels, you can project your data to a higher dimension. But the idea is like if you take your data to higher dimension, it can be linearly separable. So here they are like going to project the data into 3 dimensions. And now you see like the data can be separated with a plane here. So this is, I think, a nice visualization. So I think you get the idea why you would want to up project your data sometimes. Not always 2-dimensional data reduction, right? So, I mean, if your data is linearly separable, you can then build a simple classifier to get the decision boundaries. So, and that's why it's important. So, we want sometimes P greater than equal to 2, like greater than or equal to, like in masked autoencoders generally is equal to D. So a trivial solution in denoising autoencoder, in an autoencoder, if you set P greater than or equal to D, not in denoising auto, like in a normal autoencoder, if you set P greater than equal to D, then there's a trivial solution. You can just copy your vector into the latent code, right? But that's not what you want. So denoising autoencoder randomly masks some of the input features, but reconstruct the original uncorrupted input vector, right? So then the trivial solution does not exist now. So any questions about denoising autoencoder? I hope it's clear. Yeah. So this is some ways of doing denoising. Adding noise to your data. Here they are masking some of the pixels, and here they're adding some Gaussian noise. Generally now in modern self-supervised learning, we use this type of technique where we mask some patches of the images, for example. So I think this paper is pretty popular called masked autoencoder. I think you have probably heard about this from Florian. So in this model, you mask your input image, you mask patches. So you basically divide your image into small patches and you mask some of those patches, right? Uh, the unmasked patches go to the encoder and encoder learns some representations of those unmasked patches. Then you add back the mask patches and the decoder gives you the embeddings. Basically, decoder reconstructs the target image. Right? So this is an example of denoising autoencoder, which is pretty modern and pretty popular. Here, actually, it's pretty interesting that the encoder only looks at the unmasked patches, right? But the encoders still have to basically learn the contextual representation or the context of these unmasked patches. Like it has to learn which context these unmasked patches belong to in order to reconstruct the image. So this is a key idea also, like in word to vec style, you basically try to predict what the context of a word is, right? To learn word embeddings. I think, are you guys familiar with like word to vec, word embeddings? How do you learn word? So it's a pretty similar idea, right? Like you have some word and, so there's a question? Yeah.
Yes. If the encoder has to learn the context of the path patches anyway, why do they make it necessary to add it back in after the encoding? Like, why not just trust the encoder to learn everything that path straight through?
I mean, yeah, I think that's the method that was used earlier. Just send this whole mask thing to the encoder and then let it reconstruct, right? I think that's a completely feasible option, but it's inefficient. For example, now, so in this paper, for example, they were masking 75% of the data, right? So the encoder generally is a transformer. So the sequence length that goes as input to the transformer is the number of patches you have. So now if you're only focusing on the unmasked patches, then you have a much shorter sequence. So just for efficiency reason, they did this and they found like the model performs as well as if you put all of your data into the transformer. So yeah, I think that's a good question. And actually this technique is now used in most modern self-supervised learning methods in audio and speech as well. Where you only process your unmasked patches through the transformer, and then you have a very lightweight decoder that gives you representations of the masked patches, right? That basically the decoder is connecting the masked and unmasked patches together. but it's much lightweight than the transformer. So the most computational cost is in the transformer, right? So yeah, this is basically, I wanted to say that this is an example of denoising autoencoder, which is an old idea, but used in modern self-supervised learning. Yeah, any questions on this? I think this is a pretty interesting idea, and this is applied to like most self-supervised learning methods now in different fields.
Now it's calculated.
Yeah, sure.
Because they are taking out the mask.
Sorry, can you say that again?
For the encoder, do they specifically engineer the positional embedding so it reflects? Like...
Yeah, I think that's a great question. I think in the paper, so I'm not sure actually, but in the paper, I know that there's a similar method that is applied to speech self-supervised learning. There, they try to engineer the positional embeddings, try to like add back the positional embeddings for the masked parts, later on after the transformer, after the encoder, and they found like there's no such benefit. Like you can just ignore those. Yeah, but yeah, I mean, basically, you have some positional embeddings in the beginning, right? You can try to add those positional embeddings back here, but it does not really matter if you do or not. I'm not sure like why, but that's what the data to VEC. There's a paper, data to VEC 2.0, which was published like last year or 2023. They tried to do this positional embedding thing, and it did not help them.
Like I can ask you, the idea is that you put the position encoding in your inputs, and then you copy the proper position encodings to your encoder. So you skip the masked ones,
yeah,
and then you add them back in your decoder as if you were doing vision transfer. Yeah, it would be aware of the position. Yeah, yeah. But as it was said, also the position embedding sometimes it's not that important.
Yeah. Yeah, I think. Are you familiar with like the MAE paper? Did they do this thing that you are saying? Okay. Yeah. Oh, okay. Nice. Okay. Okay. Nice. Yeah. So, I mean, sometimes these papers are trying different things, and whatever works. Like there's sometimes no justification like why it's. I mean, you would think that it would matter, right? Like adding positional embeddings. But yeah. Any other questions on denoising autoencoders or this masked autoencoder in particular? So here, there's no like low dimensional latent code, right? But this is an example of an autoencoder. Why is it an autoencoder? Because you're reconstructing your patches, right? So there's a mean squared error loss between this and, for example, this patch. So these are like representations of the patches coming from the model, and you are computing a mean squared error between this and this. Yeah. There are variations of this in other fields that I'll talk about, like in audio and speech in particular. So a little bit of some details. So as I said, like a large subset of image patches are masked. So 75% of the signal is masked. So if you send only the unmasked patches to the transformer, it's much more efficient to process. So as I said, the encoders only apply to visible patches, and masked tokens are introduced after the encoder. And full set of encoded patches and masked tokens processed by a small decoder. The decoder is generally pretty lightweight, so just for efficiency reason. And then, like, how do you use these things? After you train this, your encoder learns a contextualized representation of your high dimensional data. You can use this part for your downstream applications. So generally, you can use it for image classification, segmentation, all those high level classification tasks. Okay. So yeah, that's how these things are applied in practice. So another example of denoising autoencoder, pretty common. I think you are probably familiar with BERT, right? So in BERT, you mask some input tokens, which are subword units, and then you try to predict the ID of those subword units, right? That's another example of denoising autoencoders, which was very kind of revolutionary in 2018. 2018, yeah. But also the key idea is denoising autoencoder. So this denoising autoencoder or masked autoencoder idea also exists for audio, which is pretty recent. I think 22. Here, instead of image, you have an image-like 2D representation of the speech or audio signal, actually, which is called the spectrogram. And you mask those the spectrogram. You basically divide the spectrogram into small patches, like 16 by 16 patches, and then you mask those patches. And you have, again, the exact same architecture as the masked autoencoder for images. The encoder only processes the unmasked patches, and then there's a lightweight decoder and a mean square error loss between the predicted patches and the true patches. So denoising autoencoder, state-of-the-art audio representation. So actually, this was trained on general sounds, not speech. General sounds like environmental sounds, all the sounds that you hear, car sounds, etc. That's a pretty big research area as well. So later, I'll talk about a variation of this masked autoencoder idea, where instead of predicting the image patches, you actually predict some semantic label corresponding to those image patches. Because if you are doing this mean square error loss between the image patches, like the spectrogram patches and the predicted patches, your model is still incentivized to learn fine-grained details of your signal, right? In order to reduce this mean square error loss. But you might not want to do that. I mean, this model is already not a good generative model. So why are you trying to do this? Why are you incentivizing your model to learn fine-grained details of your signal by doing this mean square error thing? So instead of doing this loss, you can replace your ground truth patch with some semantic label, with just a token. And that's a state-of-the-art methods, self-supervised learning methods for speech or, like wave to wake, for example, data to wake, etc. They do exactly like that. But it's also kind of denoising autoencoders, right? Yeah, go ahead.
Just a question. I don't know whether you know the details of the previous example, but
sure.
What kind of encoder have they used? Are they going for a transformer like in Vision? And the patches are rectangular?
It's actually exactly. Yeah, the encoder is the vision transformer.
Okay. So
and the patches are created just like you do for a to put as input to the vision transformer.
Because my intuition would be that, as we discussed also in previous sessions, that the dimensions of the spectrogram are not the same, right? You have time versus frequency.
Yeah.
So if I would do this, I would try to tinker a little bit with it. So have they done any studies on this?
Not in this paper. And there's another paper called Beats from Microsoft. They do exactly the same thing also. So I think there's so when you're modeling sounds, not speech, right? When you're modeling sounds, people have found that using a vision transformer like architecture and dividing your spectrogram into patches works best. You don't really need, in speech, you don't really need this temporal information. It's closer to the image if you are working with general sounds.
Okay.
Yeah.
Because you are just looking for some general short.
Yeah, you can say that. Yeah. I mean, there's obviously there's some temporal dynamics. Obviously, if you have multiple sounds, there are multiple sound events and there's temporal dependency between them. But I think since 2021, people have been using vision transformer for modeling general sounds. And this paper also does exactly the same thing that the masked autoencoder for images does. Yeah, I think in audio MAE, I'm not sure if they use. Yeah, sorry, go ahead. Can I just answer this first? Yeah, sorry. For the audio MAE, actually, I'm not sure if they use the transformer, but because MAE, the image model does not use transformers, right? It's a CNN, right? The example that I gave you from 2021.
They try both.
Okay.
Yeah. Oh, I'm not sure.
Yeah. So, okay. But anyway, I mean, the goal is quite similar. But there's another paper after audio MAE that uses vision transformer. But yeah, go ahead. Sorry.
Sure, whether you code it or I sleep. But when you in inference time, when you have the whole picture, when you don't have and you don't need any patches, so how do you?
I think in inference also you convert your image into patches. it's just a deterministic process. Like, for example, if you have a image, HW, so it's a deterministic process. You just have like patches of 16 by 16, and you have this kind of sliding window. So yeah, I mean, during inference also you convert your image into patches and then process it through the transformer if you're using transformer. Yeah.
But in this encoder, only a subset of the image fits once. The whole image.
Whole image.
So it's flexible on the input size.
Sorry. Yeah, the input size can be big. Yes.
More than that variable.
I mean, so for sound modeling, they generally model only 10 seconds. So they know like they can only model 10 seconds. It's not variable generally. That's like a way to get around in these papers. They just say that all our sound samples are 10-second long. Yeah, so they either pad it to 10 second or trim it to 10 second, but so they know a fixed length. Yeah. So again, like this would probably not work for speech, yeah, for sounds, this is like generally a standard thing to do, like 10-second long. Okay. Sorry, go ahead.
Okay, just
sorry, there's another question.
Check the paper is only transformer.
Only transformer, right? Oh, in the MAE, this paper? Oh, okay. Oh, that's interesting. I thought it was resonance. Yeah. Okay, sure. Yeah, sorry.
My question is that I think there are two strategies to masking.
Yeah.
Thing, like one strategy is to mask the input with a certain percent.
Yes.
And this approach is to mask the representation. Do you think like the difference between these two approach and what representation are they learning from it?
So I think they are also masking the input, right?
Oh, it also masks. Oh, I see.
This yeah. The input to the encoder. Yeah, I mean the input is masked. Yeah. So I mean, what the model is learning is, for example, what is the context in which these patches exist, right? So it's all about contextual learning. You look at all successful self-supervised learning methods, they're learning contextualized representations. Like BERT, for example, is learning what this masked word is in context of the sentence. So it's kind of similar. Like you can think of this as a sentence, and you're learning what these patches should be in the context of this sentence. Yeah. Sorry, go ahead. I mean, that's like how I think about it, but there may be a better way to think about it.
So I just want to ask, is the masking rate also they use the same as the image masking?
Yeah, actually, they use the similar, yes, 75%. Yeah.
And would there also be a default masking rate for audio data for sounds?
They use the same rate, yeah. I think they might have tried with other, like generally, masked autoencoder like methods for audio use a pretty high masking rate, like 75% and so on. So yeah. Even for speech modeling, masking rate is pretty high when you're modeling speech with some other SSL methods. Any other questions on this? I think it's a pretty interesting idea. Like it's actually used in a lot of things. Okay, so yeah, I think this was actually an overview of, but yeah, I think so we covered the autoencoders and the denoising autoencoders, right? So now let's look at some other technology, variational autoencoders. Any questions on the autoencoders, denoising autoencoders, etc.? Right? No. Okay. So variational autoencoders are different from autoencoders. Unlike autoencoders, VAEs are a generative model. And the general structure here is you have some, again, you have some data vector X, some encoder that outputs, instead of outputting a latent code, it actually outputs a distribution over the latent code. So you would here have from your encoder distribution, which is a posterior distribution over your latents. The decoder, so then once you have a posterior distribution over your latents, you sample some Z, that's your latent code, right? And you send this latent code to the decoder, and the decoder also outputs a distribution over your data. And then you can sample your data from this this distribution. So the bottleneck, again, this thing is called the bottleneck, the Z thing, also gives a low-dimensional latent code. The encoder and decoder are also neural networks. Again, just like autoencoders. So I think just to understand variational autoencoders, let's start with some basics on variational inference. Not sure if yeah. Okay, yeah. So basically, variational autoencoders can be understood by considering this generative model that is shown here in the slide, right? So, are you guys familiar with the generative, like probabilistic graphical models? Yeah. So this is just a graphical model. There's a latent there's a latent code underlying this data. So there's always this assumption that there's some low-dimensional latent structure that is generating your X. Here I'm showing if you have n samples, then you would represent your graphical model like this. Every data point in your data set has some latent representation, Zn, right? For simplicity, I'll just represent this as Z and X, like these are, you can think of them as random variables, right? So the goal here is to learn this generative model. What does that mean? Like what would happen if we learn this generative model? We can generate from this model by using this process. So we first sample the latent structure from some prior distribution over the codes, and then we sample the data point conditioned on that latent structure. We can also do inference if we have the posterior distribution. So given some data point X star, we can infer the latent code. I think this type of thing you have probably seen in automatic speech recognition, right? Yeah, you have some object P of Y given X, and you do this kind of inference. So if you can learn this generative model, you can do these two things. So this thing, PZ given X, is called the posterior, and then the prior over latents is PZ, and this is called the conditional likelihood, actually. So if we have these three things, we can do generation and also infer the latent code given some data point, right? So let's focus on the posterior, and then we'll get at how you can learn this generative model using autoencoder architecture. Are you guys able to see actually? Probably not. What should I do? Okay, I guess. I think there's most of the math is in the slides as well, but I just wanted to go slowly on the board, just so people can understand better. Yeah. So yeah, let's focus on the posterior distribution. Like, how would you get this posterior, right? Because as I said, this is important to infer the latent code given some X, that you can use this posterior for doing that inference. So this thing can be written using Bayes rule like this. This P of X is this thing. I think these are just basic probability rules, right? So P of X is generally intractable. So you cannot actually compute P of Z given X using this thing. Because Z is generally high dimensional, you cannot do this integral. It's intractable. I think that's the problem that variational inference tries to solve. So what variational inference does is approximate this P of Z given X with some Q of Z given X, right? And then you want to find Q. So Q Z given X is a family of distributions. So for example, if you assume that Q is a Gaussian, then the parameters, so the family of distribution means that different parameters of that Gaussian will lead to different members of the family, right? So you want to find a Q in that family of distributions, which is closest to this true posterior. And there's a thing called the KL or the I forgot the full form, Kullback-Leibler divergence, right? This thing. Let's see what this thing is actually. Yes, I can go here now. Yeah, for you guys, I can throw it on the slides. As I said, like this you can get the posterior using this formula, and the denominator is intractable. This denominator, by the way, is all like P of X is called model evidence or marginal or model likelihood. There are different terms for this term. I think you will see like maybe you have heard of evidence lower bound. That will come because this term is called model evidence. So we approximate our posterior with some tractable distribution Q, for example, a Gaussian. And this is a family of distributions. And we want to find some Q that fits with the posterior. Okay. So basically, this is the formula for KL divergence. So KL, Q, and P. So Q and P are two distributions over some random variable Y. And that's the formula. It's basically Q log Q by P. I think probably you have seen it in some classes in information theory or something. So we can write this KL between the tractable distribution and the posterior using this formula. Right? We can do some calculations and like massage it a little bit to have this form. So this basically KL between the tractable distribution Q and the true posterior is basically the KL divergence between the distribution that we know of. So tractable distribution means that like we know how to sample from it and how to evaluate if we have a point, like how to evaluate the density of that point under this distribution. Right? So you have these two terms if you compute the KL. There's a KL term here. So KL divergence is basically closeness between two distributions. It's not a distance because KLQP and KLPQ are not equal to each other. But yeah, you have these two terms. One is the scale between Q and P, right? Sorry, the prior over the latents and the posterior, the tractable posterior that we created over the latents. And an expectation term here, which kind of looks like an expected log likelihood, right? And there's this constant term, log P of X. This just falls if you do some mathematics here. So you see here, if you rearrange, so KL divergence, another property of KL is that it's always greater than equal to 0, always positive, right? So if you put the KL greater than equal to 0, then you see, you get this thing. And it basically, you get this bound on log of P of X, which is the model evidence, right? This thing is called the evidence lower bound. By the way, is it like completely intractable for you guys right now to understand what's happening? So, you know, we started with this goal of, yeah, sorry, go ahead.
Just clarify the motivation.
Yeah, I think it will become clear, yeah. So the motivation, first of all, is why we want a tractable distribution is because the posterior we cannot compute, right? Because of this term. I think that's clear, right? Is that clear or no? Yeah. Because this denominator is, you know, this high dimensional integral, which is very difficult, like a sum over a high dimensional Z. So for example, let's say your Z is a d-dimensional binary vector. So the number of configurations that Z can take is 2 to the power d, right? D is generally pretty high dimensional, like 100 maybe. So 2 to the power 100 configurations. So you have to compute this sum over 2 to the power 100 configurations. So it's not tractable, right? Even just 100 is not tractable, but generally Z would be probably like 200, 300, 400, whatever, right? So this thing is intractable to compute. So you cannot compute the posterior. So we want to approximate the true posterior with this tractable distribution. So we know how to do things under this distribution. We know how to compute the expectations. So for example, that integral that I was talking about, I can compute it under this distribution. Right? I can also sample from this distribution. So basically, I want to approximate the true posterior with this tractable distribution Q. Right? So how would I find this Q, right? I need some kind of measure of closeness of Q with P, for example, or measure of closeness between two distributions, right? And then I can optimize over that, right? I can say that give me Q, which is closest to the true distribution. So that closeness measure is called KL divergence, right? That's a measure from information theory. And this is the formula for KL divergence. If you have two distribution Q and P, you compute the KL between those two using this formula. Y here is some random variable that these distributions are over, right? So here I'm just showing, like, if you open the KL divergence between Q and P, Z given X, these are our distributions that we want. You can do some math here. I mean, if you want me to explain these steps, I think it's easy to see, like, for example, here I'm just using this formula to get this thing, right? Here, I am doing, what am I doing here? That's why I wanted to do it in the board, so I can actually follow my own steps, right? Yeah, so here I'm just expanding this thing with Bayes rule, right? And just separating these things out. And here I am, basically taking this P of Z. So this becomes log P of Z, right? And this comes here, the P of Z. So this becomes a KL divergence again, right? So this becomes a KL between Q, this posterior and the prior, right? So this is the formula for KL, right? Log Q minus log P. So actually, maybe I should have written the formula like this. So the KL between Q and P is Q log Q over P, right? So that's the thing here, right? So this becomes a KL between this Q and this P. So that's what I've written here, right? And this thing is an expectation under this distribution. So I've just written that as EQ log P of X given Z, right? And then there's this extra term, which is a constant actually, log P of X. Then, so here's a KL here, right? This KL is equal to this thing. I can put this as greater than equal to 0. So there's this property that KL is always greater than equal to 0, right? You can actually prove this. So I just put this thing as greater than equal to 0, right? In this equation. So I just put this greater than equal to 0, and this is greater than equal to 0. And then I get a bound on this quantity, log P of X, right? And since it's a bound on the evidence, I said that this is called the model evidence also. So this is called the evidence lower bound. Right? So here I'm just like replacing this thing, this whole thing with minus evidence lower bound. There's some math here, but I mean, it's not that crazy, right? Like this thing is in that equation. I'm just putting this with the name elbow. That's commonly how it's referred to, right? So now KL, I have simplified it to negative elbow plus this constant term. This is a little bit clear or still,
I guess Katrina was asking, what's the motivation here?
Yeah.
I suppose the motivation is that Q is currently a free choice.
Yes.
And you're going to choose Q to minimize that KL divergence on the left.
Yeah, exactly.
Okay.
So,
yes, that's the motivation.
Yeah. So basically, yeah. So when we do this, all this calculation, KL between Q and P, right, we get this kind of equation where we have this elbow and there's a constant here. So if we maximize this thing, we are basically minimizing this thing. Like this is what we wanted, right? To find some Q that will minimize this thing, right? Actually, we cannot directly minimize this, right? Because we don't have this thing. So we need some bound or some kind of other function that if we minimize, then we know that this, if we maximize or minimize whatever, this thing will be minimized, right? So we want some other function. And that function is this evidence lower bound, right? This thing, because it's constant, if we maximize this, this will be minimized, right? So that's the motivation. Like we set out with this tractable Q that we wanted to find, and we can find it by saying that, oh, how do we find this Q, right? We can minimize the KL divergence, but how do we minimize the KL divergence? Because KL divergence is also intractable because of this P, the true posterior, right? So we find this new function that if we maximize, then the KL will be minimized. So that's actually what the variational inference is all about. Right? So now we can just focus on the evidence lower bound, right? So this evidence lower bound has these two terms, and let's see how we can actually maximize this thing. Because remember, we want to maximize it so we can minimize the KL between the tractable posterior and the true posterior. So these two terms are actually pretty similar to now. Okay, so there are these parameters theta and phi in this term that we want to optimize. So Q has parameters phi. As I said, like Q is a family of distributions parameterized by some parameters phi, right? And this first term also has some parameters. So this P is some function that takes Z as input and then tries to produce X. And Q is some function that takes an X and tries to infer the latent code. So now can you guess like what kind of structure this is, right? So P is taking Z, like the latent code, and going to X, and Q is taking X and going to Z, right? So this is kind of autoencoder, right? So you can do this optimization using an autoencoder structure.
So Samir, if I pause you for a minute.
Yeah, sure.
Should I think now that without the phis and the theta, this was just some generic distribution P of X given Z, which is true in nature.
Exactly.
Q of Z given X, which you are going to choose. You can choose anything under the sun.
Exactly.
And your goal is to maximize this quantity on the right.
Yes.
And you chose to parameterize them.
Exactly. Yeah. And we'll sorry, go ahead.
And you're going to parameterize them both in such a way. First, you're going to parameterize them in some sensible way. And
with a neural network.
Parameterize them. You're going to choose the parameters to maximize this.
Exactly. Exactly.
Okay.
So yeah, exactly. So I hope that probably clearer, as Sanjeev said. So I think you can also guess what these thetas, what this P theta and Q phi, like how would we parameterize it? The answer is like with neural networks, obviously, right?
I was going to say, before that, you could even start giving them names. What does P do? P takes a Z, maps it to an X.
Yes.
That's your decoder.
Yeah, exactly. So I mean, I just wanted them to come up with this, but
Okay,
so that's, so that's like so that's the decoder of your autoencoder, right? And the Q would be the encoder, right? So, and as you guessed it, like it will be neural networks, obviously. So yeah, that's our optimization of function. So now we parameterize these things so generally we would fix the prior to some, standard normal. You can also learn this prior. Maybe I can touch on that a little bit, but let's say we have the standard normal prior, which is fixed. Right? This function is also a Gaussian. This, the decoder or the conditional likelihood is also a Gaussian function. And the mean and the covariance are parameterized by some function f, which has some parameters theta. The posterior is also a Gaussian, right? We want tractable things, right? Otherwise, there's no point. And that the parameters of this Q are parameterized by this G function, which has parameters phi. And, both of them are deep neural networks. So we can actually simplify this further and see that it is more of an autoencoder, right? So this thing, P theta X given Z, since it's a Gaussian, it has this exponential term, right? So Gaussian density has this term, minus mu squared, right? If you take the log of this thing, then these things come out and becomes a reconstruction loss, right? So I just replace that with this thing, reconstruction term. So this thing can be replaced with a reconstruction term because in the elbow you had this log P of X given C, right? So in elbow, you have this term, expectation log P theta X given C. If you take the log of P theta and if it's a Gaussian, then you'll just have the exponential term, right? So it becomes a reconstruction loss actually, just like an autoencoder. And there's this extra term, which we just call it a regularization term. And regularization term, intuitively, why is this important actually? Can you guess why this term is important? If you think about variational autoencoder, our goal was this thing, right? Our goal was generation. We want to sample from the prior and then generate X. So this is the generative process of the VAE. And the inference process is we won't have P, obviously we'll sample from the tractable posterior. But why do you think this regularization term is important? Yeah, go ahead.
It's well behaved.
Yeah, exactly. What does that mean exactly? Like well behaved, yeah.
So because we want to use this model to sample new data.
Yeah, exactly.
And we want the latent space.
Yeah, exactly.
To have a certain shape, to sample the data from some region, which is the unit Gaussian.
Yeah. That's
or is the distribution of z's to sit there. The z's that correspond to x's that we actually have in our data set.
Yeah. So yeah, that's the answer basically. Perfect. So what the answer here is like basically your decoder is learning to generate X from Z, which is sampled from the posterior, right? But during a generative process, we don't have X. We want to actually generate X, right? So we can't really get Z from the posterior, from the Q, right? Q of Z given X. We actually can only sample from some prior distribution. So we want this posterior to be close to the prior also. So during sampling, we can actually, when we sample from the prior, we get like samples which are close to our data, right? I hope that's clear. So if you know nothing about VAE, like how we arrive at this elbow, etc., you just have these like two terms to make it a generative model. To make an autoencoder a generative model, you need a reconstruction term and also this regularization term, which makes your prior close to the posterior that your neural network will give. Is this clear? Like this, intuition? I think you don't have to really know the math. Like this intuition is enough, probably. Yeah. I mean, that's how I think about VAE. And maybe there's a better way to do it, to think about it. Yeah. So VAE is also an autoencoder, right? But it's a slightly different kind of autoencoder where the encoder, the G phi, this is your encoder, outputs like these distributional parameters for your posterior distribution, which is a Gaussian. Right? You sample from this posterior, that gives you this latent code, right? And then there's a decoder that tries to reconstruct the input vector, the input data. There's a reconstruction loss, just like in autoencoder, and there's a regularization loss on the latent space to make this Q posterior close to the prior, right? So we can sample from it later on and generate new data, right? So that's your variational autoencoder. So do you see any problem here? Like if you are training with backpropagation, because these are neural networks and you want to train them with gradient descent, backpropagation in particular. So what's the problem here with this? Yeah.
Sure. So I guess the sampling.
Yeah, exactly. Yeah, exactly. So the efficient sampling algorithms, if you want to sample some data from a Gaussian distribution, all the efficient sampling algorithms have some hard decision that you have to make. Like I think a stupid sampling algorithm is rejection sampling. And you have to accept or reject based on some. So if you make a hard decision, then this process is not differentiable. Is that clear? Like if you are making some hard decision like argmax or argmin, it's not differentiable, right? That function. Okay, I think that's probably clear. So basically, I mean, if you look at the computational graph, like if you're thinking about implementation, so in backpropagation, so this is a simplified diagram of this variational autoencoder. So decoder, encoder outputs some distributional parameters that goes to the sampling box, and out comes the latent code that goes to the decoder. So when you're doing backpropagation, you'll have some upstream gradient coming from this direction, right? And that's basically the gradient. Oh, that's opposite. So delta L should be here. So it's basically the gradient of the loss with respect to this Z here. Right? That's the upstream gradient during backpropagation. And then when you are doing backpropagation, you multiply this upstream gradient with the local gradient, right? That's the backpropagation algorithm. So this local gradient delta, like change in Z, given some change in the input mu, which is the parameter, right? This is not defined. So you cannot backpropagate to the encoder, right? But there's an easy way to make this differentiable. You just have to sample it in a different way. It's called the reparameterization trick, which was like proposed in 2013 paper in VAE. So in the reparameterization trick, so again, there's a mistake here. this should be here. And yeah. So yeah, so this is the sampling process. You can sample from a Gaussian in this way also, right? Like you take your mean and the covariance of the Gaussian, and you sample some IID samples from a fixed noise, standard normal, and you can, oh, I did not write it. Okay. I think I have it. Yeah, you can sample like this, for example. If you want a sample from a Gaussian which has this mean and covariance, you can get a sample like this, mu plus epsilon, where this thing is just sampled from some standard normal. So this is just a noise. Right? This actually makes your computational graph open. So now you can backpropagate. So, the plus operator is just a distributional operator. So this will just distribute to these two branches in the computational graph, this gradient. So you have a gradient from here to here, right? And you have this local gradient, the gradient that is going to this covariance function is actually scaled by this epsilon. Because like if you have a multiplication operator, then the gradient, so so if you have z equal to xy, right? And you want to compute the derivative of c with respect to x, that is basically y, right? So the local gradient will be epsilon, right? The local gradient here between these two is this thing. So the local gradient is multiplied with the upstream gradient, and you get this update quantity. Yeah. Is there any confusion in this? How we get around this non-differentiability thing in VAEs? Yeah, please.
So I understand.
Yeah.
I understand how this version is differentiable. What makes the previous version not differentiable?
Because
still sampling from a Gaussian.
Yeah, I mean, if you don't sample like this, then it's non-differentiable. But I mean, I was just saying there are more efficient sampling algorithms. Like if you go to NumPy and you do np.randn, this is not the algorithm that they use. There are more efficient algorithms that have to make some hard decision. Like if you are using rejection sampling, are you familiar with some sampling methods? There are many sampling methods, and yeah, people actually work on coming up with more efficient sampling methods. And mostly the sampling methods that are efficient for Gaussian have some hard decision that you have to make. And so that is non-differentiable. Yeah. That's what I was saying, yeah.
So what we've been doing so far, all of this has been differentiable, or?
This is all, if you sample like this, using this thing, this is differentiable, yes, as I showed here, yeah. Because you have these plus and multiplications, yeah. There's no argmin or argmax. If you have those type of things, then it's non-differentiable. So this is called the reparameterization trick, pretty popular. If you are working on VAEs, you will hear this often.
So Samir, in summary, it looks like whatever the upstream gradient is, it goes through as is to mu.
Yes.
And sigma actually gets some random epsilon as its update. It doesn't even depend on z actually.
I mean, the upstream, it depends on the upstream gradient, and it's scaled by the epsilon.
It's scaled by
it, yeah. Because if
of course, it's scaled. Okay, got it.
Exactly. Yeah. Because the local gradient is this thing. If you have a
randomly scaled.
Yeah, exactly.
So basically, take the gradient, pass it through to mu. Take the gradient, scale it by some random
Exactly. Yeah. Yeah, that's what's happening in this computation graph. Yeah. So yeah, just to give you a sense of how this is differentiable. Yeah.
Now I can implement this.
Yeah. So I have these L and Z's wrong in every slide. Yeah. So this is called reparameterization.
Just look at the slide upside down.
Yeah. So that's your variational autoencoder. Any question on VAEs? I think, yeah. So after you have trained the VAE, then you can use this thing, the encoder part only, to get some latent code and do some downstream task, right? Just like we do in all unsupervised learning methods. Yeah, sure. Go ahead.
What does variational mean? I know what is autoencoder, but
I mean, variational is the evidence lower bound, right? That's your variational objective, right? Yeah. Okay. I think And the autoencoder means that you are using autoencoder to implement this variational, like optimize this variational lower bound. Yeah. This elbow thing is called the variational lower bound. Yeah.
Like what I want to say, like the thing that I didn't get when I first learned this is,
yeah, sure.
and it's like the crucial central part of this, and it has to do with the term variational, as I understand it.
Yeah.
Is the fact that the encoder does not produce the Z.
Yeah.
It produces a distribution of Z's. Yeah. And I don't pass the Z directly to the decoder when I'm training, but I take it as the distribution from which I sample.
Yes.
So I get a different Z.
Sure.
And then I pass it.
Yeah.
So when I hear variational, I think like the encoder produces something that then gets varied a little, and then I pass it through. That's how I understand it.
I mean, but like in an autoencoder also, you can add like Gaussian noise to your latents, and then like the latent is following some Gaussian distribution, right? So variational, yeah, I mean, I understand your explanation. I just think like variational comes from like this variational lower bound that you're optimizing. But yeah, I mean, as I said, like there are different interpretations of these. Yeah, so I completely agree with your interpretation. Yeah.
Can I just add, because when I was learning this, just to be technically correct, it's producing the parameters of the distribution, not the distribution. So.
I mean, it's a similar thing, right? No?
But I was always wondering whether we could use some different distributions.
Yeah, I think that's a great question. Yeah.
But yeah.
So yeah, I think that's a good point. Like, can you use any other distribution, like instead of Gaussian? Like, what are some things that you would need to take care of if it's not a Gaussian distribution? Like
you can say that the Gaussian distribution is like the uniform that's not bounded. It's like the most most generic distribution. So that's why you can use it.
Yeah.
Unless you have some specific task.
Yeah.
Like maybe if you had some crazy latent space, then maybe you would come up with some different distribution.
Yeah. I mean, definitely like some people, I mean, it does make sense sometimes to do learn a discrete code instead of a continuous code, right? So, I mean, we'll get to the VQVE, I hope, soon. But basically, the thing that you have to take care of is that you should be able to reparameterize your sampling process so that it's differentiable, right? You can actually compute the evidence lower bound, even if you have like a discrete distribution, like a categorical distribution here. But so I'm not sure if I want to get into that, but the gradient estimator will have a very high variance, and if you do the reparameterization, the variance of your gradient estimator is reduced. This is just an aside, like if you're, reading some papers, they talk about these things like the gradient of the variance of the gradient estimator. But yeah, I think we don't have to get into this. But yeah, I mean, if you're interested in like learning more about variational autoencoders and all these like nuances of, which estimators have higher variance, etc. I think there's this guy, Rajesh Ranganathan, who did his PhD on this like black box variational inference at Princeton. So I mean, you can read his thesis. I think it's pretty good.
Samir, let me make one more comment.
Yeah,
if you really want to know where the name variational comes from, right? There's this method of optimization called variational calculus.
Yes.
It involves making small changes to functional.
Yeah.
And if you read that, you'll see the connection to what Samir just explained.
Yeah.
And that's where the name comes from.
Yeah.
Comes from variational calculus.
Yeah. So take the class on probabilistic graphical models. They talk about all these things. Yeah. So yeah, I mean, after training the VAE, you can take this encoder and then, get the latent code by sampling from the posterior and do some downstream tasks. Generally, what people do in practice is actually not sample from the posterior. They just take the mean that the encoder is outputting. That's like the general thing that people do. Also, you can then, once you have the VAE, you can generate new data points from this VAE. You just sample your Z from this standard normal and then generate the data vector. And generally, again, people just out-generate the mean. They don't actually generate the distribution over X. That's something, I mean, when I was working on VAEs, I did try to learn the variance. And it's generally like very unstable when you're training, when you're outputting both the mean and the variance of your over your data points. I don't know why. Some people just put their variance as like a parameter. They don't actually, it's not dependent. It's not given by the neural network, but it's just a parameter that is also trained. These things don't have much of an impact. So generally, people just output the mean of this Gaussian and keep the covariance fixed, the distribution over the data. So VAE, as I said, like it's an old idea, but now it's used with diffusion models. So this is a popular example called audio LDM or audio latent diffusion model. Pretty popular paper now, 2023. So here, like the VAE is used with diffusion, right? So latent diffusion, generally there's this issue that if your data is high dimensional, it's difficult to build a diffusion model, right? So what people generally do is compress their data into some low dimensional code and then model that with the latent diffusion. So if you have a VAE that is pre-trained, right, you can take the latent code from the VAE encoder, which is like downsampled. So this is a downsampling factor. So it's a compressed version of your input data. Input data will be C cross T cross F. T, time dimension, F is frequency bins in audio, right? So yeah, you can model this with latent diffusion. And then after you have trained your diffusion, you can run the diffusion process, get the latent code and pass it through the decoder of VAE and get your audio. So this is how like VAEs are used nowadays. I'm not aware of like a standalone VAE model that is like state of the art at something, but it's like used with this diffusion thing. Yeah. I think earlier in 2021, 2022, people tried to build VAEs alone to do self-supervised learning, but they have not been successful. Yeah. The most successful idea for self-supervised learning has been masked prediction or masked autoencoding. But still, VAEs are used these days. Okay. Any questions on VAs? I think we can move to the vector quantized VAEs. Yeah. But yeah, I think we need to take a break, but like, let's just go through some introduction of VQVAE. So VQVAE is pretty simple. All of the autoencoders have the same structure. So in VQVAE, you have some encoder that is embedding your X, transforming your X into some latent representation. Then you quantize this latent representation using a vector quantization module, and you get this ZQ, right? And this quantized embedding then goes into the decoder to reconstruct X. These are the losses, and we'll talk about these losses, how you optimize the VQVAE. Actually, optimizing VQVAE is much more challenging because you cannot actually get over this differentiability, a non-differentiability problem easily. So actually, the solution is pretty weird, but it works. Actually, this is VQVAE is pretty often used in many applications these days. Okay, so we have still a few minutes. So for VQVAE, this is the structure that we'll focus on, and we'll see like how we can train this model or build this model, and what are these code books. But are you guys familiar with k-means algorithm? Yeah. Okay, great. So this is just like the cluster centroids of the k-means in the bottleneck, right? So you get some embedding from the encoder, some low dimensional embedding. I'm calling it the pre-code, right? So this is not the code that we want, but we map this pre-code, this is a continuous vector, to one of these cluster centroids, if you will, or codebook entries, just like in k-means, right? And then you get the embedding of that code. So let's say you map this pre-code to this small k cluster centroid that has an embedding associated with it. And that's your latent code, ZQ. Right? That goes to the decoder. And then you try to reconstruct this input data. So that's your VQVAE. But let's look, we'll look at like how actually you do these operations and how this is like really non-differentiable. And the solution is really weird, I think, but it works really well. Yeah, I mean, maybe you guys can explain me, why maybe it makes more sense to you, this operation that they do to get rid of non-differentiability. Actually, they don't get, yeah. Okay, so I think we can take a break probably. Yeah. Okay, yeah, sure. Okay, yeah. I think probably this is the right time. Yeah.
Okay.
Yeah.
Let's take a 15-minute break.
So VQVAE is another autoencoder, but the goal here is to learn a discrete representation of your data. So kind of like clustering, if you're clustering your vectors with k-means, you map those vectors to the cluster centroids based on the distance from those centroids, right? It's a similar goal here. So you have some input vector, the encoder outputs some representation of this data, generally low dimensional than the input vector. And then you map this representation from the encoder to some codebook entry. These codebook entries are just like the k-means centroids, right? Once you have found the closest match in this codebook, you output the embedding corresponding to this code. This embedding is the embedding of the centroid in k-means, for example. And then you pass that to the decoder. And the decoder tries to reconstruct, right? So any question on this basic structure of VQVAE? Yeah, sure. Yeah, I mean, that's a good point. Compression, right? Like if you are compressing your data into a discrete representation, then you're using less bits to encode your data, right? So you can have a high level of compression with quantization. And sometimes, and sometimes like it's also better, like if you're doing generative modeling, as I'll show, if you have like tokens corresponding to images or audio, then you can just train a language model, right? Like GPT, for example, as your expressive prior, right?
The variation of the encoders also like the issue of using right images or not?
Yeah, for sure. But there's methods. I'll explain. Like there are some new methods called that uses generative like adversarial training for training these VQ bottlenecks, and also residual vector quantization that actually leads to very high fidelity synthesis. So there's no blurriness because of the GAN, like the adversarial training instead of the MSC loss.
So like with your code embedding, basically you have like K code embedding.
Yeah.
So what's the difference between this and just having like a regular sparse order encoder? Like the top K feature.
Yeah, I think that's a valid, feasible option as well. I'm not sure why people don't use sparse order encoders. Does anyone have any comments on this? I mean, it's a old idea, sparse order encoders, but I feel like it has never really worked that well. VQ idea is also old, like 2017 from DeepMind. I mean, I'm not sure like why not do sparse order encoding and do this, but most of these things are also experimental, like whatever is working better. Yeah. But recently, I mean, if you're interested in sparse order encoders, like OpenAI and other labs are using sparse order encoders to understand the activations of their neural networks. So maybe you can look at that literature. But yeah, I think maybe it's making a comeback, sparse order encoder. I'm not sure. Yeah.
I think what the usage for the codebook is that in the training of VQVA, you have also minimization of codebooks and all of the instances.
Yes.
So like we're trying with the semantically relevant vectors are also given in the loss to minimize the distance between the codebook and all of those instances.
I mean, sparse order encoder also learns like a dictionary of features. Yeah, I mean, it can be a valid option. Yeah. Okay. Any other questions on this basic? Yeah, go ahead.
How do I then sample from the code book?
Sorry?
How do I sample from the code book when I'm...
You cannot. So this VQVA is not a generative model. We have to actually train a prior after we have done this compression. Then you can sample from it. So how, I'll show an example actually of...
what's the use for it if it's not generative?
I mean, you can generate from it. So as I'll show, but you can't, like a VAE, you can build the generative model along with the autoencoder training. But here you have to do it in 2 steps. Yeah. Okay. First step is compression. Second step is training a prior on the codes, which like this, I'll show some papers that do that. Yeah. But you can generate from it. Yeah.
Yeah. How do you get the centroids for the k-means? Do you update it?
Yeah. So that's the next few slides. Yeah. This was just, I was just explaining what VQVAE is. Yeah. Okay. So these are, you can express VQVAE mathematically like this. So you have ZE, which is the embedding outputted by the encoder, encoder transforms X into Z. Then you compute the distance between this embedding Z and each of the entries in the codebook, right? So this CK is the codebook embedding. And this is just the Euclidean distance between the two embeddings, right? You do that for all your codebook entries, and then you pick the argmin, whichever is closest to the Z, and that's your code. That's your discrete token that you assign to Z, right? And ZQ is just C of K. I mean, it's just the embedding of that codebook. Yeah. C is the, yeah, exactly. C is, let's say you have K codes and they are, d-dimensional. Each code is d-dimensional. Then C would be a matrix of K cross D. So this is VQVAE, in equations. So do you see any problem with training this with backpropagation?
Yeah.
Yeah, exactly. So I think the solution will surprise you. So yeah, encoding, then this process called codebook lookup. So you are looking up which code is closest to Z, right? Because you want to assign some code to Z. Then reconstruction from the decoder, condition on ZQ, which is the code embedding. So the in K means, is the centroid embedding, right? One of the losses is the reconstruction loss again. Right? So this operation is non-differentiable as pointed out. So why? So, again, the same issue, upstream gradient cannot be multiplied with the local gradient during backpropagation because the local gradient is not defined. It's a non-differentiable operation. I hope it's clear like why this is non-differentiable, why argmin would be non-differentiable, right? So the solution is actually pretty simple. You just copy the gradient from this to this. And this is called the straight-through gradient estimation. I'm sure there's some like theoretical reasons. I mean, so straight-through estimation was not invented by the VQVAE authors. They actually point to some old paper from Bengio in 2012 or something, and I have not read that paper. But yeah, I mean, what do you think about this solution? Just copying the gradient from here to here. Sorry. Yeah, it's a biased estimator. Yes, it's a biased estimator, but which could have high variance, but it works in practice. There are some other losses that are used to make the training stable of VQVAE, and I'll show you those losses. But this is what VQVAE does, like to get around the non-differentiability thing, just copy the gradient. And this, by the way, is like the state-of-the-art compression algorithm right now. I mean, some variations of VQVAE, but the basic idea is still the same. So yeah, I mean, how you implement this in like software, for example, when you're doing the assignment, you basically do something like this. Not sure how to explain. So yeah, so this is like a way to copy the gradient from here to here, right? So you implement this in this computation graph. So ZE is subtracted from ZQ, and you detach this part from your computation graph. So nothing will go here. No gradient will go here. And then you add back ZE, right? So what is being passed here is ZQ actually to the decoder that we want, right? But because of this plus, now the upstream gradient will be distributed and will be copied to ZE. And nothing will flow here because this part is detached from the computation graph. So this is like a way to practically implement when you do the lab assignment, how you implement the straight-through operation, right? If you do this kind of thing, then the gradient will automatically be copied to Z, right? Because of this plus here, right? And remember, plus is basically a distributor of gradient. Right? Is this operation clear? By the way, like in PyTorch, for example, if you're doing like, it will be ZQ minus Z dot detach, right? Plus Z. So the gradient can be copied to Z. I hope this operation is clear as well. Yeah, nice. Okay. So there are other losses in BQEAE, something called the codebook loss and the commitment loss. So let's look at these losses a little bit. If you guys have like a better understanding of these losses, please let me know. But the codebook loss is what is it doing mechanically is the stop gradient here is applied to Z. So Z is fixed. Z is the target for ZQ. This means that the codebook vectors are updated to move towards the encoder outputs, right? So we are learning this common space or alignment between the encoder output and the codebook embeddings, right? Because codebooks have to be in the same space as the vectors that you're quantizing. Otherwise, quantization would not be very good, right? The representation will not be good, and the reconstruction will also not be good. So there's another loss, commitment loss, right? So commitment loss is now here the stop gradient is applied to ZQ, which is a codebook vector. So this ZQ corresponds to the codebook vector that you choose for the ZE. So the commitment loss ensures that the encoder output, ZE, stay close to the chosen codebook vector ZQ. So in the codebook loss, all of the codebook vectors are updated, right? But in commitment loss, only that codebook vector, the ZE is updated only using the codebook vector which is closest to ZE. So the alignment between, so this points to the alignment between the encoder outputs and the codebook vectors. And this is crucial for stable training and effective representation learning. Because if codebooks and the encoder representation space are like completely disjointed, then the quantization will not make sense. And the proper alignment also ensures that the discrete representations are meaningful and capture the essential features of the input data. Yeah, go ahead. Yeah, exactly. Yeah, if you're familiar with k-means, I think you would identify this as two steps in the k-means, like where you update the centroid and then update the parameters. That's similar, yes, for sure. There are some alpha and beta scaling factors on these losses. So they have to be like, you have to find those things out by doing a lot of experiments. Generally, like for the commitment loss parameter, beta is like 0.25. Everyone uses that for some reason. And alpha is generally 1, I think. But yeah, I mean, this model has, I guess, I'm not sure if it has a theoretical basis because of the, copying of the gradients, etc. So you have to do some things to make it work. And in the earlier times, it was very difficult to make it work, actually. Yeah.
I mean, I've not stared at this long enough to have good intuitions, but what it looks like is that the first part where you do the codebook loss, right?
Yeah.
That really is like k-means. You're going to update your code points, your CQs.
Yeah, exactly.
Based on what Z's align.
Exactly.
The second point is a bit weird because k-means you normally change the boundary.
Yeah.
Right? Decide which one belongs to which one.
Exactly.
It's a bit more like you're changing the ZE itself.
Yeah, exactly. So
that's because you're in this funny setting where unlike k-means where the ZEs are fixed.
Yeah, exactly.
Here your Z itself is a variable.
Yes.
Given the code points, do you want to belong to the ZQ or not? If you don't, then move over a bit to the other side.
Yeah, exactly. Like, yeah, it's a little bit weird and probably, I guess, to be honest, like I don't have a very deep intuition about this. But yeah, please let me know if you guys know more about this. Sure, thanks. Okay. So I think I already explained commitment loss, ensures that the encoder output does not drift too far from the quantized codebook vector and encourages encoder to produce outputs that are close to the discrete codebook entries. Right? So as I said, like without this alignment, encoder could produce vectors that are difficult to quantize, if they're not in the same space, right? Leading to poor representations and reconstruction. Yeah, similarly for the codebook loss, I already explained this. Okay, so let's look at the codebook a little bit. I think these are now interesting things that some state-of-the-art methods will try to improve. So if there are k codes in your codebook, then basically you are using 2 to the power, if there are, Yeah, if k is so, if you want your if you want to quantize your vectors with k bits, then you would need 2 to the power k codebook entries, right? So if you have 1024 codes in your codebook, then basically you are saying that I am quantizing my input vector, the incoming vector, with 10 bits, right? Any doubt about this? I think it's probably clear. So yeah, sorry, go ahead.
Like the index of the code.
Yeah. So if you have like 1024 indices in your codebook, then you have 10 bits that you're using to quantize your Z, the incoming vector. So let's say if you want to use 20 bits, right? Because 10 bits can be very less information to encode all the details of your input high dimensional data to reconstruct it faithfully. Like audio signal has a lot of details. Like if you are thinking about high fidelity audio generation, then you probably need much more bits than 10, like maybe 80. 80 is a good number in some state of the art paper. But for 80 bits, you need 2 to the power 80 codebook entries. So it's not possible, right? So we'll see like how you can get around this issue with residual vector quantization. But I hope it's clear, like if you keep increasing the number of bits that you want to encode your incoming vectors, then this is intractable, right? The codebook will explode. So 2 to the power 20 is not possible. Some terminologies that people use in the papers to evaluate how well the codebook is, how good your codebook is after training is codebook entropy. So I think this probably pretty simple, right? That's just a formula for entropy. Basically, the maximum entropy for the codebook is log k, because the maximum entropy would be for a uniform distribution over the codes, right? So generally, people report this number, codebook utilization, which is a relative entropy corresponding to the uniform distribution. Right? Is there any doubt on this? Just some formula for entropy I've written here, and then I have shown here that what would be the maximum entropy that this codebook will have, and that will be if the distribution is uniform. So I've replaced the pk with 1 over k if there are k codes, and so it gives you log k, right? And then this is called codebook utilization, which is actually reported a lot in the papers. Generally, you would want codebook utilization to be very high. So you would want most of your codes to be used for encoding your data. So yeah, there are no questions on this, right? I think we covered it. So yeah, this is a prominent paper, like a seminal paper in 2017 at NeurIPS from DeepMind, which introduced VQVAE. So here, the input doesn't have to be a vector. So for example, in their case, it was an image, 3 channels, and the size of the image was 128 by 128. The CNN encoder compresses this image into a low dimensional code, 32 by 32 by 256. So there are 32 into 32 256 dimensional vectors that you will have to quantize. So all of these vectors are quantized using a codebook, and then you get this 2-dimensional map. From this 3-dimensional map, you get this 2D map, right? Is this process clear? Like how we are going from this image to this 3D feature map? So the 3D feature map is just like you have, the simplest way to think about this is you have 32 by 32. 256 dimensional vectors, right? So these are your ZEs. These are your ZEs. You have 32 into 32 ZE vectors that you want to quantize, right? So as Sanjeev mentioned earlier, like the input doesn't have to be a vector. The code doesn't have to be a single vector, right? It's generally a feature map. And then you quantize this feature map into a 2D map. In this map, these are the code entries. And then, so this is 32 by 32 by 1, because you have compressed it to some discrete codes. And then you send it to the decoder, and the decoder tries to reconstruct. Decoder is generally the transpose of the encoder. But I hope this operation is clear. The ZE, 3D to 2D, and then ZQ will be 3D again, right? You'll replace these codes with the corresponding code embeddings in the codebook. So this is the paper that started it all, and it's a pretty popular paper now. Yeah.
So each
Is the quantization done pixel independently?
I mean, I think I'm trying to understand your question. So the whole image is kind of transformed by this CNN into this feature map. There are 32 by 32 feature map. There are 256 of those. Sorry. Yeah.
What is the blue square? I forgot what you called it.
Yeah, the discrete codes like tokens. Tokens. Yeah. Yeah, exactly. Yeah.
So one integer specifies a given code.
Yeah. So this, for example, this integer corresponds to this 256 dimensional vector.
Right.
Yeah.
Vectors.
Yeah, exactly. Yeah. So there's a code book. There are entries in the code book, which are the integers, right? The tokens here. And each entry has an embedding, just like k-means centroids, right? We quantize these incoming vectors z with this codebook by finding the closest match using Euclidean distance. And then we assign that code and we get this discrete token feature map, if you will. And then we get the quantized representation ZQ by replacing these IDs with the code embeddings. You can see the color also, like purple color is coming from the codebook, right?
So it's like image size independent, right? Because it doesn't have to be significant. It can scale to any size.
Yeah, for sure. Yeah. You can have like any size here, yeah. Okay, so this is the VQVAE paper. So let's look at the compression factor, right? So the input, so this is in terms of bits. So the input will need 128 by 128 by 3 by 8 number of bits, right? So this is the shape of the input. And each pixel can take values between 0 and 255. So you need 8 bits to encode a pixel. And then for our codes, it's 32 by 32. And each code is 512 dimensional. So it requires 9 bits to encode each code, right? Sorry? Yeah, I think I got it wrong. It has to be 512, yeah. Because that is 512, yeah. Oh, no, sorry. I'm sorry. It's 256 dimensional, but there are 512 codes. So you're basically using 9 bits for this quantization. Sorry about the confusion. 256 is the dimensionality of the code embedding, but the number of codes is 512. So there's 9 bits here. So the compression factor is actually pretty huge, 42 times compression if you use VQVAE. And actually, if you look at the paper, you are able to reconstruct pretty well with just this small code book. So with this high level of compression, you can still generate pretty good things. I mean, in your lab, you will generate these things, and you will see it does look like you can identify some objects, but as I said, like now we have pretty good quantization algorithms, which can generate pretty high fidelity. So the bottleneck here is that they can't increase the size of the codebook too much, right? They know that 9 bits are probably not enough, but they can't really increase it because the codebook will explode. So if you want to encode your images with 20 bits, then the 2 to the power 20 would be the size of your codebook. So it's not possible. So now coming back to generative models. So once you have the compression algorithm, how do you build a generative model? It's pretty easy. Like you have this discrete map, right? It just consists of tokens. You can model with some autoregressive modeling. So I mean, mathematically, what you're doing is you have some discrete tokens, right? That's all your image is now. So image is, let's call it Z actually. Z1, Z3, right? So your image X is transformed into some Z, which is just a map of discrete tokens. So it just consists of these discrete tokens, right? And you are trying to model a density function on these discrete tokens. So you would just do autoregressive modeling, right? Just a chain rule. 1, and so on. I think you guys know the chain rule, right? So this architecture is basically implementing the chain rule in a more efficient manner. This was like an early work called pixel CNN. This is a pixel CNN. But here, instead of pixels, this CNN is on these discrete tokens. Much easier to train, much faster because it's much more compressed. It's only 32 by 32. So yeah. Actually, this image I copied from Pixel CNN. So it's showing like the density here, the conditional density that it's modeling is outputting intensities from between 0 and 255. But in our case, this would be like a softmax uh, vector, like a distribution over 512 codes, right? Is this clear to you? Like, no? So how would you model discrete tokens? I think that's the question. Like, how would you model density of discrete tokens? Yeah. Gumbel softmax, yeah, I think I won't cover that, but yeah, that's another way of doing vector quantization. But I'm not covering it because it's not very popular right now. Yeah, it's not, this method works pretty well. But I was just talking about like once you have the compression algorithm, like you have a way to transform your images into like discrete tokens, how would you model the density of those tokens after, like in stage 2, for example? Yeah. Sorry? I mean, so let's say we have a sequence of tokens. So, we have a data set with like a sequence of tokens, like we have in text. How do we model the density of these tokens? Yeah. So this one is just a map of tokens, right? You can just like compress. So if it's a 32 by 32 map, you can just flatten it. And like that's your sequence of tokens, right? That's how you can do it. Sorry, go ahead. Yeah, you can use a transformer for sure. In this paper, they used a different architecture called Pixel CNN because they did not compress it into a sequence. They just modeled it with this 2D structure. But this 2D structure is actually doing the same thing, predicting the class of this particular code, like what should be the distribution over this time step. I mean, not time step, like some kind of a step, right? Conditioned on all the previous classes, right? Yeah, exactly. It's a language model, a 2D language model. It's called Pixel CNN. But yeah, I mean, that's how you model density of discrete tokens, right? Like autoregressively, you can model it. So this is an autoregressive model where you predict the distribution over a particular point conditioned on all the previous tokens that you have predicted, right? So that's how you build. So now you have this model in stage 2. You can actually sample from this model. It's a density model, right? You can actually sample a sequence from this model, right? So let's just like in GPT, right? In GPT, if you build GPT, this is GPT, right? It's a density model over discrete sequences. You can sample from this model. That's how GPT generates data. So once GPT is trained, during inference, you input some tokens, and then you ask GPT to generate the next token, and condition on that, you generate the next token, right? So you can generate tokens from this model as well. This is just an autoregressive model, just like GPT.
That's the message yeah, I see it as a blue square, right?
Yeah. Once we have the blue square, we train this thing first.
Just with just vectors.
Yes. Yes. Yeah, exactly. Yeah, exactly. So here, you have a more complicated token sequence. I mean, if you want to call it sequence, a map, token map, and you are just doing autoregressive modeling on that map. And then once you have this model that can give you that basically gives you distribution over your codes, you can sample from that, and you can send that sample to the decoder and generate image, right? So you can build a generative model easily with this as well. So is it clear like how you build? Yeah, sorry, go ahead.
Yeah. So this, you've got like a transformer really like the next.
Yeah, actually, I'll show an example with the transformer. So this is an old paper, but newer models are actually doing transformer. Yeah.
Like, so you've got a sequence representing one individual image, but let's say you like stacked bunch of images together.
Yes.
And that sequence of stretch those images.
Yeah.
Could you do the same thing? Basically predict the next sequence and then decode it. Like,
yeah, for sure. I mean, I'm not sure like how Sora works, but probably they're doing some compression and then, modeling with transformer, because that's the state of the art method right now of doing generative modeling of images. So yeah, but who knows how they build that model, right? But yeah, I mean, you can definitely do that. Yeah. Okay, so, so the transformer. So now the state of the art method is this method, which is called VQ-GAN. So there's still vector quantization bottleneck, but there are two differences. So first is that these token density, this density estimator over token sequences is not a pixel CNN, it's a transformer, right? And instead of doing the mean squared error loss to optimize your VQ architecture, the encoder decoder, you have a GAN, adversarial training. So I won't go into the details of GAN, but maybe somebody covered it earlier in this workshop. But basically in GAN, so in mean squared error loss, like in the normal VQVAE, you take the reconstructed image and you compute a mean squared error loss between the reconstruction and the true image, right? So the input image and the reconstruction, there's a reconstruction loss here. But in GAN, you have some discriminator that analyzes this image. And basically the job of the discriminator is to figure out whether this image is fake or real. If it's fake, if the discriminator says it's fake, then there's a high penalty on the decoder. And so the decoder has to learn how to reduce that penalty, right? So the decoder eventually learns how to generate good images by playing this game with the discriminator. So the decoder's job is to fool the discriminator so that the discriminator does not put a high penalty on the decoder, right? That's GAN basically. There's a lot of math behind GANs, but that's the idea, right? So so this is the state-of-the-art technique. Again, the encoder gives a 3D feature map, which is quantized into this 3D embedding map, right? Here in between is the 2D discrete token map, which is modeled with the transformer instead of the pixel CNN. So you just flatten those 2D discrete map into a sequence, and then you just build a transformer. And the transformer is just this density estimator, which is modeling these conditional densities. So what is the probability of a particular token given all the other previous tokens it has predicted? So that's this equation tells you. Any question on this? This is like now applied to all other fields, this method, like audio, speech, whatever, and it's working pretty well. Yes, it's still autoregressive, yes. Yeah. So yeah, I hope it's clear like how you can use compression models to build a generative model as well, right? Like VAE does not give you a generative model straight away, but you have to do this second step where you model the prior over these. So for sampling, you need prior, right, over your latents. And here you learn the prior afterwards. This is expressive prior that you're learning. In VAEs, the prior was pretty constrained, and there's no easy way to get a very expressive prior. You just have this standard normal. But here you can learn an expressive prior, like any neural network density estimator. So it's pretty cool. And that's why the generations from these models are much better than like the VAE model. Right, yeah.
So do you learn words to describe which is
Exactly. Yeah. So yeah, I think that's a good intuition. So what the compression algorithm is doing is embedding, like representing your image patches with some discrete tokens. And what the transformer is doing is capturing dependencies among those tokens, like how this image is actually created, right? Yeah. So that's the intuition in the paper as well. So you divide the image into these compressed tokens, and then you model the dependencies among those tokens using the transformer. So that's the generative model, state of the art VQGAN. There are some issues. Let's see if I have slides on that. So yeah, I mean, these are some image generations from this model. Like this is the conditioning, and then these are the generations. So by the way, when you are training the transformer, you can also condition it on some other external signal. And they condition that transformer on these type of things, like the segmentation map. And given the segmentation map, the model learns to generate things that are contextually relevant with this map. Similarly, given the skeletal structure, this is contextually relevant to this structure, and similarly for this and that. Yeah. So these are some examples from the paper. Okay, so there are some issues with vector quantization. In particular, the issue of codebook collapse. That's a big issue that is studied in every paper, where basically what happens is that your model, that your none of the codes or very few codes in your codebook are actually utilized to model the patterns in your data. So we generally want a high utilization of the codebook, so we can learn more nuanced patterns in the data. So there's a very simple idea to get around the codebook collapse. But let me first, sorry, I think I jumped ahead one slide. So yeah, this is another state-of-the-art method that came after VQGAN. It is called improved VQGAN. In this, they have, instead of the CNN encoders, they use the transformers, also for compression. So in this, idea, the compression is done with CNN, right? And the autoregressive modeling of tokens is done by transformer. But in this, they use for compression also the transformer, and for autoregressive modeling also the transformer. So, vision transformers are pretty popular now. So you can just map these images to patches and then use the vision transformer to get embeddings for these patches. You quantize these embeddings with the codebook lookup, and then you have a transformer decoder. And then there's a GAN objective for training this whole pipeline. This is a pretty interesting idea also. I think just replacing things with transformer everywhere. Yeah, go ahead.
So these become sharp because you are a discriminator.
Yes.
Because that's the way trained was function that analyzes.
Exactly. Yeah. It's the not mean squared error. Mean squared error will incentivize the model to give you mean of the images, right? It will regress to the mean. But discriminator can actually give you signals of more fine-grained details. And also, how you set up discriminators is pretty complicated, and I'm not getting into the details. But yeah, I mean, having a simple discriminator will probably not do the job. Generally, the discriminators are analyzing the signal at different scales, so there are a lot of details there also. Yeah. So as I said, there's this issue of codebook collapse where not all the codes are utilized to capture patterns in your data. If you have more codebook utilization, you can capture more patterns in your data, right? That's the simple explanation why you would want to have high codebook utilization. So a simple method to avoid codebook collapse, which was proposed in this paper, is you get these pre-code embeddings, right? These are the ZEs here. These things are the ZEs. You quantize the ZEs to get ZQ, right? So before quantization, you actually do this linear projection. So you make these this pre-code embeddings smaller dimensions. So if this is dimensionality 1024, these things after projection will be dimensionality 8 or 32 or something. Very low dimensionality. Then you do the codebook lookup in this low dimensional space. So this is 32 dimensional. So you map these 1024 dimensional vectors into this 32 dimensional space, and you do code lookup in this space. Then after getting the code embeddings, so you quantize your vectors, these low dimensional vectors, to some codes, and you get the embeddings of those codes from the codebook, and then you project them back. And that goes into the decoder. So there's an extra step of linear projection to some low dimensional space. and doing codebook lookup in that space, and then upsampling them and sending them to the decoder. I read the paper, and I think it's not a very good explanation that they give. Yeah, so I don't have a good intuition about this. It's just that it works pretty well. And in the paper, there's one paragraph on factorial codes. So factorial codes mean that like the codebook lookup and the embedding are decoupled. So this is the codebook lookup process, which is low dimensional. And then the embedding is still high dimensional, because you upsample the code embedding to high dimensionality, and then you send it to the decoder. So basically what they're saying is that the code embedding and the codebook lookup process is decoupled. So I mean, I actually don't have a good intuition about this. So, but I just wanted to let you know that this is the method to improve codebook utilization, and it is also used in other papers like for audio modeling, etc. Yeah. Yeah. But number of codes here is like 8192, right? So you mean like yeah.
The codes are high dimensional.
Yes. Okay.
There's just a few of them.
Okay.
There might be an issue because the space of all the single codes is large, but we have just a few codes.
I see. I see.
Shrink the space so that the number of codes for covers the space, it might work better.
Yeah. I think so. I mean, in some paper I read like it's similar to PCA like thing. But yeah, I have to think more about this to get a better intuition. But yeah, sorry about that. But yeah, I still wanted to mention this because it's a very important method. So just by doing this, the codebook utilization improves a lot in their paper. I think I have some results here. So for example, if you, where is it? Yeah, so this is basically the latent dimension tells you about this, how much linear projection you're doing, the down projection you're doing before the code lookup. So if you, I think this one, for example, 256, this has no projection. Like this is the normal VQ process. And they're getting a pretty bad codebook utilization. But if they actually embed their code into 32 dimensions and then do codebook lookup in that low dimensional space, you will see the utilization is generally higher, right? 95, etc. So that's the ablation analysis over whether to do the projection or not. So this 256 is doing no projection, like it's just doing code lookup just in the normal VQVAE sense. But these other things are doing low dimensional code lookup, right? I hope the low dimensional code lookup process is clear. So, let me explain with like a simpler. So you have a ZE, right? Some vector that you're quantizing into some code K and then ZQ, right? So here you are first projecting ZE down to some low dimensional thing, like let's call it ZE1. So if this is like 1024 dimensional in this paper, these Z's are 1024 dimensional. They're coming from this transformer. No, actually 768 dimensional, I think. So yeah, but whatever. 768 dimensional is projected down to 32 dimensions. And then you do the code lookup to get the K. And then you get the ZQ1, which is also 32 dimensional, obviously. Then you upsample it to 768 dimensions, Z to get ZQ. That goes to the decoder. So this is like the extra step added in the VQ bottleneck. Right? So you project it down and then do the lookup, then upsample it or up project it. I hope the process is clear. Any questions on this? Yeah, I mean, if you're doing vector quantization, you should probably do this for sure, because in many papers, this is working, as they show here also. Yeah. Okay, so residual vector quantization. As I said, like if you want to increase the number of bits that you want to use to encode your incoming vectors, it's not possible because there will be a codebook size explosion, right? So if you want 20 bits to encode your incoming vectors, you need 2 to the power 20 codes in your codebook. So one way to get around this is called residual vector quantization, which is like another method which is used in all the state-of-the-art compression algorithms now. So in residual vector quantization, the idea is pretty simple. I think I don't have Sorry. Okay, so let me explain this here. So in residual vector quantization, the idea is like you have multiple code books in series, right? So you first compress your incoming vector with 10 bits using one code book. Then you compute the difference between the quantized embedding and the incoming vector. That's the residual. So that's something that your first code book is not able to capture, right? So that's leftover. Then you quantize this residual with another code book with another 10 bits, for example. Then you compute the residual again and you keep doing quantization in series. And that actually increases the number of bits that you're using to encode an incoming vector, right? So let's see. So you have some ZE coming in. You quantize it to ZQ, right? So this, let's say this you're using here a codebook size of 1024. So you're using 10 bits to encode this incoming vector. Now you take the residual. So that's your ZE minus ZQ. I'm sure there's a better way to make this thing. So yeah, there's a VQ1, let's say, that gives you ZQ. And then VQ2. VQ2 basically takes the difference between ZE and ZQ, right? And then that goes into VQ2. Let's say we just have two quantization layers. You get, this is ZQ1 and this is ZQ2. So let's say this code book has 1024 codes. So 10 bits is the capacity of this code book. And this code book also has 10 bits capacity. So the total bits that you're using now to encode this incoming vector is 20 bits, right? But you don't need a code book of 2 to the power 20 codes. You just need two code books of 1024 codes, right? Yeah.
Background, say background that's something.
Yeah, for sure. And by the way, like so this is your module of residual vector quantization, right? This thing is your RVQ module. And what comes out of this, which goes to the decoder, is basically the sum of ZQ2 and ZQ1. Right. So I hope the intuition is clear. Like what you're doing in residual vector quantization is whatever is not encoded in these 10 bits, you're taking that and then quantizing that thing, right, with 10 more bits. So essentially you are using 20 bits to encode this incoming vector, right? So that's simply residual vector quantization. Yeah, go ahead.
So it reminds me of processor caches because in a cache you also
yeah
lines and you can
yeah
because you can have 20 bits. The question is into how many steps
yes
or how many bits you have.
Yeah, exactly. So residual vector quantization is not a new idea. Like vector quantization, residual vector quantization always existed. I'm not sure like why people started using it so late. I'm not sure. So yeah, in residual vector quantization, generally what happens is the first codebook encodes more high-level structure, and as you go closer to the decoder, the codebooks become more and more fine-grained. So more fine-grained information about the signal, which is required to reconstruct the signal faithfully, is encoded in the further quantization layers, like the quantization layers that are closer to the decoder. So this paper actually, no, this paper did not introduce it. There's a paper in audio domain that actually introduced residual vector quantization. But let's stay with images, right? So how this will work is now, let's say you have, I just assume that you have, actually they have 4 code books here, but I just assume they have 8 code books, right? So the image, again, 128, it's actually 2 reduced by 2. But anyway, there's some image, right, that goes to some low dimensional representation. And then you quantize it. Remember in VQ, where you just have one code book, you have 32 by 32 by 1, this feature map with discrete tokens. Here you have 32 by 32 by 8, if you have 8 residual quantization layers, right? So now compression is less. It's not as much as we saw in the previous one. So let's assume that the input image is 128 by 3, 8 bits to encode each pixel. And now we have, instead of 32 by 32 by 9, we have another multiplier 8 here, which corresponds to the number of code books we have in series. So now we are quantizing our incoming vectors with 72 bits instead of 9 bits, right? Just by doing this residual quantization. Right? Yeah. Yeah. Okay. So just 2 codes. Yeah. Yeah, I mean, that could give you some interesting interpretability, but yeah, I'm not sure. Nobody has tried it. Yeah.
So you have to optimize the number of code books.
Yeah. No, I am generally, if you look at the papers, it's like all the code books have the same number of codes. So all the code books are like, doing 10 bits, for example. But yeah, I think that's an interesting idea. Like you can have less bits in the beginning code books and more bits in the higher quantization layers. Because as I said, like the higher quantization layers are encoding more fine-grained details of the signal. So you need more bits there. But you can reduce the number of bits in the first 2 quantization layers, for example. Yeah. I mean, I have actually some experience with this, and generally codebook usage is increases as you go up because, as I said, like the upper codebooks have to encode more. Yeah. Basically the quantization layers that are higher up have to encode more fine-grained details, right? So the codebook utilization there is higher than the codebook utilization in the first quantization layer. So that's pretty interesting, yeah. Yeah, I wish I had some, like, there are some examples of RVQ where they show, like, if you only send the first few code books to the decoder, the model generates some high-level structures. And then once you add more code books, then you can also generate more fine details. So that's the decoupling that the model is doing when it's doing residual vector quantization. Yeah. Yeah, so actually the paper that introduced RVQ is this 2021 paper from Google called Soundstream. Their goal was to compress audio into these compressed representations, and they did use RVQ and also the GAN objective to train this model, the adversarial training to train this model. Yeah, so in their case, they're showing here NQ is the number of quantization layers in their residual quantization module. So I mean, I think I don't need to focus on this architecture, but let's say you are trying to compress the audio into these discrete tokens using residual vector quantization. And this is from Soundstream paper again. So you have some input waveform at the top here, which says waveform at 24 kilohertz. There's generally like a block of convolutions that downsamples your signal to something that is manageable, like 75 hertz. So I think maybe you guys are not familiar with this terminologies. So if you like, audio is generally when you store it in digital form, it has some sampling rate, right? 16 kilohertz is generally used for speech, and then if you are downsampling speech to, for example, 75 hertz, then you're doing a lot of compression, right? Not sure how else to explain this. Yeah. But basically the point is that this convolution modules are doing a lot of downsampling by a factor of 320 generally. 320, 512, 160, these are general downsampling factors from these convolution layers. Right? So you can see like the stride is also pretty big, right? 2, 4, 5, 8. So the total downsampling factor is 8, 40, 320 here. So you just multiply the strides and you get the downsampling that this module is doing on this waveform. So yeah, the downsampling is pretty heavy. Generally, that's the case when you are dealing with waveforms and you want to get some representations. Okay, so then this downsampled representation is not going anywhere. But yeah, so just showing the encoder decoder. Obviously, between the encoder and the decoder, there's a RVQ, residual vector quantization module. But yeah, decoder is generally just the transpose of the encoder. The decoder blocks have transposed convolutions. So that's a general framework that is used everywhere. You have encoder, and decoder. If the encoder is CNN, then the decoder will be CNN, but with transposed convolutions. And you see the striding factor is also just reversed. So 8, 5, 4, 2, and 2, 4, 5, 8. So, that's like how you generally do this style of compression. And that comes from these previous papers that I mentioned earlier. Okay. Yeah, so there's another paper, which is currently the state of the art, which uses exactly the same thing as the SoundStream. So they have the same architecture as SoundStream, but they have some more RVQ layers. And that paper is Descript Audio Codec, which is mentioned here, which is pretty recent, actually, 2024, which exact same structure, but just more RVQ layers, like more quantization layers, but also taking this idea from this image compression paper that does low dimensional code lookup, right? So they combined these two papers and came up with a much better algorithm for compressing audio. And this algorithm, DAC, Discrete Audio Codec, can actually generate audio with very high fidelity. It's not blurry or don't have artifacts, right? It's a pretty high fidelity synthesis. So let's look at the compression factor that DAC achieves. So let's say your input waveform is 44 kilohertz. So you have 44,000 samples. So your input is a sequence of length 44,000. If you're talking about 1 second of audio, right? So for encoding that long sequence, you need these many bits. Generally, audio is encoded with 16-bit, right? So you have this bit rate, right? But they compress their model. So they use an encoder to downsample from 44 kilohertz to 86 hertz, right? And they are using 9 codebooks, and each codebook has 1024 codes, so 10 bits capacity. So the compression factor that they achieve is 91x, right? But if you actually look at their audio synthesis or reconstruction quality, is pretty good. Right? Like you will not be able to differentiate between the true audio and the reconstructed audio from this codec. So yeah, then that's pretty impressive. Any questions on what's going on here, like this compression factors and things like that? So they actually compare their model with like some other state-of-the-art models like SoundStream from Google and Encodec from Meta. And they show that like they have much higher compression factor, but in the results you see like they are actually the quality of the audio is is much better than Encodec and SoundStream. It's pretty good. Yeah. Yes, go ahead. Yeah, because the input audio is like much higher dimensional also, right? If you're talking about 44 kilohertz audio, you have 44,000 samples in your input for 1 second of audio. Yeah. And there are a lot of maybe redundant structure, but yeah, I guess why is it so high for audio? Like image also, they were able to achieve like 42x, maybe they can go further with our, more compression, but yeah, I think it's kind of similar. Yeah. Again, like how they came up with this, like this is not a theoretical compression factor. It's like they just tried different compression factors. Like they tried their encoder with like different downsamplings and different RVQ layers. Whichever model was giving them the best results, they reported that. And that model achieves 91x compression. Yeah. But yeah, there's no like, oh, 90x makes sense. Right? It's just experimental. Yeah. But yeah, I that's a good question. Like why with audio you are able to achieve like much more compression. But I guess somebody will then have to do experiments with images to really tune the compression factor, right? But yeah, I haven't seen that paper. Yeah. Yeah, that's the Descript Audio Codec state of the art. Actually, in our workshop, we are also using this codec for doing generative modeling. Yeah, they did some ablation analysis again with like low dimensional code lookup. They can achieve much better utilization. In their case, actually, compared to image, in the low dimensional code lookup, in the image case, they were doing 32 dimensions. They were projecting the incoming vectors to 32 dimensions. And here, they are actually able to project the incoming vectors to 8 dimensions. So it's also much smaller. Yeah. So yeah, I'm not sure like why there's a discrepancy, why it's not exactly same, but yeah, not sure about that. I think another interesting thing, if you are really thinking about how to build neural networks, there's something called snake activation that they use, which they say that adds a better inductive bias when you are generating audio. But yeah, I won't go into snake activation, but just a aside if you read the paper. Okay, so any questions on residual vector quantization, or anything else so far? Okay. Okay, I think hopefully it's also clear like how you can build generative models if you have this discrete tokens. If you can like build a tokenizer. So this is like if you really want to think about this intuitively. So when you build language models, right? There's a tokenizer always that tokenizes your word sequences into subword units. So it's generally byte pair encoding, right? So this is a tokenizer for high dimensional data. This Descript audio codec, for example, is a tokenizer for audio. So if you're building language model, you have this tokenizer that gives you discrete tokens, and then you build language model on top of it. So it's exactly same as using a byte pair encoded tokenizer for text, basically. Right? So yeah, think about these things as like tokenizers for language model training. Once you build the language model, you can sample sequences from the language model, send it to the decoder of these compression algorithms, and generate new things. So yeah, I think I can now talk a little bit more about, yeah, sorry, go ahead. Yeah. Yeah, so I think I was just coming to the SSL, because that, yes. So compression algorithms, I'll show like in audio LM. So audio LM is one way of building generative models of audio using these compressed tokens, right? I think you are familiar with it. So when they build these audio LMs on top of these compressed codes coming from these compression algorithms, they don't have much structure, right? So that means these discrete tokens are not really able to capture high-level structure that is necessary to generate like plausible audio. And so this high-level structure is provided by these SSL codes, right? Which we call the semantic codes, right? So yeah, so as I said like earlier on in my talk, like the SSL algorithms are generally aiming at capturing more high-level structure, latent structure in the audio signal or images. And these compression algorithms are looking at capturing more fine-grained details, which can be used then to generate your signal faithfully. SSL algorithms do not aim at faithful reconstruction, right? They are just focused on capturing some high-level structural details. Like, for example, in speech, what are the words that appear and how are they arranged in a sequence? But these compression algorithms don't have to capture those details. And that's why for building audio generative models, you need both SSL models and these compression algorithms. So I think if you remember, maybe I should have copied that slide here, but that was in the beginning when I was comparing similarities and dissimilarities between SSL and compression. Yeah. Okay, so coming now to SSL, because that's also SSL model is also necessary for building a good generative model of audio, for example. So coming back to the masked autoencoder idea. So masked autoencoder, if you remember, mask some input data and then process these unmasked patches through some encoder, and then there's a decoder that tries to reconstruct the signal back. So in speech, actually, in audio field, we generally have this idea called mask prediction instead of masked autoencoding, right? So I told you earlier that instead of predicting the actual patches or the actual signal using mean squared error loss, where you are incentivizing the model to also encode more fine-grained details. You would generally predict, instead of a patch, you would predict some semantic label corresponding to the patch. So you can quantize your, so in this case, I'm talking about this paper called Beats, which is used for building SSL models for general sounds. So in this case, like let's say you have some spectrogram, you divide it into patches, and then you quantize these patches with some codebook, just like we did for vector quantization, right? So you basically, this projection layer is projecting these patches to some vectors. You quantize these vectors using this codebook, just as I explained earlier. And so now you have a discrete label for each patch, right? And you can predict this instead of actually predicting the patch. Right? Does that make sense? You remember the masked autoencoder, right? We are predicting the patches. Instead of predicting the patches, now we'll predict these labels. So we are abstracting away from these fine-grained details of how these patches are constructed, right? We don't really want that in self-supervised learning. We just want to extract some high-level structure from the data. So that's how you can do it. So this model is also kind of like masked autoencoder, right? So there's this masked patches that go. So you mask your input, you send the unmasked patches to your transformer that gives you embeddings for the unmasked patches. Then you add back the masked tokens, and then there's a label predictor or the decoder. But in this case, now you're not reconstructing the patches. There's no mean squared error loss. You're just predicting the IDs corresponding to these masked patches that you got from vector quantization. So any question on this? So this is this actually is the state-of-the-art idea, self-supervised learning idea in speech, audio, in basically speech and audio domain. Yeah. You generally predict these some kind of tokens corresponding to the masked patches. And the loss is here just cross entropy loss, right? Yeah, so the label predictor basically outputs a probability distribution over the IDs or the codebook entries, right? And you just compute a cross entropy loss from that. No, I won't go through. So another like state-of-the-art idea of doing self-supervised learning for speech also relies on this masked prediction idea. So here you have some speech waveform. You compress it with some feature extractor. So this CNN basically compresses this waveform into some, lower sampling rate features. Like, so if you have like 16 kilohertz sampling rate here, these features will be at 50 hertz. So for each second of 16 kilohertz audio, you'll have 50 feature vectors here. So what you do is now from like you mask this feature sequence and you try to predict some ID corresponding to the masked regions. How you get the IDs is again through vector quantization. So you quantize each of these features through some vector quantization layer, and that gives you the targets for prediction for your mask prediction task. And generally, you can use contrastive loss here, but I think the details are not that important. But if you are familiar with like word embeddings, how word embeddings are learned, this is actually quite similar, right? From the context, you are predicting the ID of this masked region. So, for example, if this thing is masked, this encoder is learning a masked embedding of this patch or this frame, and then you are predicting the ID of that frame. So it's like a continuous bag of words embedding model, right? Where you have like the neighboring words and you mask the middle word and you predict the ID of the middle word. It's actually quite similar. And in word embedding learning, also you have noise contrastive estimation. And it's actually exactly like that. But in word embedding learning, you have the IDs of the words already. Here you don't have IDs for these frames, so you need some vector quantization module that gives you IDs for these labels for these frames. Right. I hope you can correlate with word embeddings if you know about those ideas. The old idea. Yeah, just learning contextual representations by doing this mask prediction. Yeah, contrastive loss. So another easier way to do self-supervised learning for speech is something called Hubert, which is hidden unit BERT. So as I said, like you don't have IDs for these masked frames when you're talking about audio. You can actually do offline clustering. So you can use some signal processing pipeline to extract these some useful frame level features for audio. And then you can just do k-means on those features. And that will give you labels for your frames. Right? And then you just do mask prediction again. Actually, this idea is much simpler because there's no online vector quantization going on like in Wave2Vec, like in here. Like this quantization, this quantized representation is actually a code book that is also learned during training, just like the VQ-VAE formulation, with the commitment loss, codebook loss, etc. So that adds to the complexity. And also there's contrastive loss. So you have to sample some negative samples and you need a decent amount of computation here. Actually, computation is same in both Hubert and Wave2Vec, but you have to think about how to sample negatives, right? In Hubert, there's no negative sampling. You just have the labels offline that you get by doing k-means on some signal processing features. And then you use that as labels for mask prediction. So actually, I was quite surprised that this thing works because these labels, people tried, like in the paper, they try to correlate those labels with some linguistic labels that we know exist underlying the speech sequence, like phoneme labels. And the correlation, mutual information between those two labels is pretty low. But still, this idea works pretty well, as good as Wave2Vec, which is surprising. And I think I don't have a good intuition about this, to be honest. But if you guys have any intuition, let me know. Another like crazy idea that works actually is actually not even, you don't even have to do k-means on these signal processing features. You can just do something like this. So for example, this is an idea from Google called best RQ, right? So best RQ. So this idea is basically that you have a Wave2Vec style of architecture. You have some CNN feature extractor that downsamples your waveform to some vectors, feature vectors, right? So you quantize them through some VQ layer, right? You get the labels. You have here a transformer that learns contextual representations. You mask first, right? And then send it to the transformer that learns some contextual representation of the masked regions. And then you predict the ID from this VQ layer. But surprisingly, you don't actually have to train this VQ layer at all. It's just a randomly initialized VQ layer. And it still gives you as good results as Wave2Vec. So that's even more surprising. I think there's some deeper insight into these things that I have to think more about. But I think you can also think about it in your free time. So again, you don't have to train this VQ layer at all. Just randomly initialize layer, and you're just quantizing these incoming vectors through this layer. And so that's a completely viable approach. So in Wave2Vec, you have to train the VQ module, like that's how they proposed it. But best RQ said, like, let's not train it at all. Just keep it fixed. Right? Yeah, go ahead.
With the mic. Yeah, sorry.
Major difference between best RQ and multi-web is that yes, like in the case of best RQ, it's randomly it's a random initialization, but also like in best RQ, you don't start from zero audio, you start with a spectrogram. And
okay, yeah.
Because you start with a spectrogram and not zero audio, it makes it easier for the model to learn about like the representation of your. It's kind of like a better initialization point.
So in the, but so I think Hubert also starts with spectrogram, right? Like MFCC features. and it does k-means on it. So the clusters are learned, right? But here it's not learned at all. Like it's just randomly initialized clusters. But yeah, go ahead.
So what we mark about like to pause you.
Okay. Yeah.
Can
I see. I see.
help a lot.
Yeah, I see.
In terms of efficiency, and which equate like those things or the arrays quickly.
So okay, I think that's a hypothesis that needs to be tested, I guess. Because in the paper they don't mention this at all, like that because of spectrograms it's working, right? And I'm also not sure, do they send the spectrogram to the quantization layer, or like after going through the CNN they pass that to the quantization layer? Yeah. Okay, I see. Yeah, so yeah, there are some interpretations, why it's working. Yeah, I guess. Yeah, but it's interesting. It's also interesting that in Hubert, if you improve the quality of these labels, it doesn't improve the performance. You can see, so that's also interesting. By the way, Hubert is yeah. Sorry, go ahead.
Could you just be a bit more precise? You just said if you improve the quality of the labels, the models.
Yeah. So quality, yeah, exactly. Like how do you measure the quality? As I was saying, you can compute mutual information between these labels that k-means algorithm gives you, and the underlying phonetic labels, for example. Yeah. So that's what I mean by quality of the labels. Yeah, like how mutually how high the mutual information is between those two labelings. Yeah, that's how they quantify generally. Like that's how they compute the quality of these labels. Yeah. But yeah, I mean, these labels are pretty low level. Like, I mean, it's actually these labels, they don't have to correlate with the with phoneme labels, right? They can be very low level also and still give a pretty good learning signal, much better than if you're reconstructing the frame, right? Uh, yeah, so I mean, there's some. I think with Hubert, I can understand. Okay, even if these labels are not correlated with phonemes, it doesn't matter. Like they just have to be a bit more semantic than like reconstructing the full frame, because they can still abstract away from a lot of details if, even if they are low level. But with the best RQ, like what's going on here? What are these labels, right? So yeah, I think that's an interesting one. Maybe what, Adele mentioned about like sending spectrograms, but yeah, I don't know. Yeah. Any other questions on SSL? Okay, because I mean, this will all tie into the generative model, how you build a generative model. So all these ideas are actually crucial there, right? How much time do we have, by the way?
Normally go till 12.
Okay, yeah. So I think let me talk about, I think you get the idea of compression. There's this field of compression where the goal is to compress your or high dimensional data into some latent codes. And the goal is to have good generation, right? Like very faithful generation. So you want to encode as much information as possible about the signal into these codes. But with SSL, the goal is good representation learning. So you can use these representations into some downstream task, right? And the goal is not reconstruction. So generally, SSL methods are incentivized to learn more high-level details of the signal and abstract away from signal-level details. Okay, so how do we build a generative model using these technologies that I mentioned, like compression and self-supervised learning? So the first paper, I guess this was the first paper in 21 from Meta. Basically, they said that, let's try to quantize these layers of these SSL models and then build a generative pre-training, then do generative pre-training on these tokens, like GPT, for example, right? So generally, they take some pre-trained SSL model like Hubert, take layer 11, depending on how many layers there are. Let's say if it's a 12-layer model, they take layer 6, quantize it using k-means, and then use those tokens for building a language model on top of these tokens. These layer 6 are the features that are in the middle of the self-supervised transformers, which are pre-trained using self-supervised learning, are generally encoding like phonetic features. So if you actually do k-means on these features and you compute mutual information between these labeling from k-means and the phoneme labeling, you will get very high mutual information, like 70 or something. But with MFCC features, you will get like around 29 or something. So these are very, phonetic categories like features, right? But they also encode other structural characters like phoneme segmentation maybe, or how these phonemes are connected, like phonotactics. So these are not just phoneme categories. Okay, so this is one way of building generative model. You have some SSL model, you quantize some represent layer of that SSL model, you build a language model. Then you also have a decoder that takes those units from the SSL quantization and generates waveform. So this decoder has to be fine-tuned separately. So this is generally like a GAN, a big GAN model that is conditioned on these tokens and that generates the waveform. So that's the first idea of how you can build a generative model for audio. So here there are some issues with this. Sorry. Let me just explain this method a little bit. So the encoder can be like a pre-trained Hubert, and you do k-means on layer 11 of Hubert. And this is called semantic token extraction. Then the decoder would be a hi-fi GAN in particular, which is conditioned on these units. Right? The language model ULM is basically just like a GPT or any autoregressive transformer trained on these tokens. So it's a density model of these semantic tokens, right? So ULM is like a prior that you can sample from. And if you can sample sequences from this prior, you can then send it to the hi-fi GAN to generate the audio, right? That's the generative model of audio. So GSLM, generative spoken language modeling, that's the model called. It shows high temporal coherence. So if you listen to the generated audio, it actually sounds like a proper English sentence, for example, with proper syntax and grammar. But audio quality is actually very limited. The speech sample from GSLM is limited to a single speaker and in a clean setting. That's not desirable. And because the model is trained on these high-level semantic tokens, as I said, like this SSL models, they abstract away from very fine-grained details, right? So you don't have much control in your generation. So for example, hi-fi GAN is trained on like a LJ speech data set. It's just single speaker and very clean setting. So as I said, semantic tokens do not provide these fine-grained details to the decoder, hence audio quality is limited. But on the other hand, tokens from like the Descript audio codec, like these compression algorithms that I mentioned, and SoundStream, they capture a lot of fine-grained signal details, but they are not good for achieving good temporal coherence while generation. So you can see like this complementarity between these two types of tokens, like semantic tokens and acoustic tokens, right? Acoustic tokens come from the compression algorithm, semantic tokens come from the SSL algorithm. So they are complementary. So there's a model called AudioLM from Google, which came in 22, that combines these two tokens to build a really interesting generative model of audio. So I think you might have guessed it, like there's a semantic token conditioning for modeling the fine-grained acoustic token. So it's not a rocket science, but let's look at this, how they build this model. So, but combining these two tokens in AudioLM leads to improvements over this GSLM model that I showed earlier by generating speech continuations that preserve original speaker's identity and intonation. So, unlike GSLM, which only can generate one speaker and very like robotic kind of voice, this is actually much more unnatural. So AudioLM, as I said, extracts two types of tokens from audio. One is acoustic tokens, which you can use this compression algorithm that I explained with residual vector quantizer layer. So these are the fine-grained tokens, acoustic tokens. And then the SSL model. In their case, they use a model called wave-to-vec BERT, which is like a combination of wave-to-vec and Hubert. But it's some SSL model, which is trained the similar way as I explained earlier. You take semantic features from some intermediate layer. Generally, that layer is in the middle of this SSL model. You do k-means on it to get the semantic tokens. Right? So you have these two types of tokens, and now you can build a generative model. This result actually shows that these two tokens are capturing different types of information, right? So this here, the column phonetic discriminability is whether your features are more phoneme-like. Lower score means your features are more phoneme-like. Higher score means your tokens are less phoneme-like. So you can see like semantic tokens are more phoneme-like, so more high level, and acoustic tokens are not that great. Right? So that's the complementarity that they showed in the paper and why these two tokens can be used together to build a generative model. And similarly, reconstruction quality with these fine-grained tokens is much higher than the reconstruction quality with these semantic tokens. Right? So this is how you can build AudioLM. It's a multi-level generative model. First, you model semantic tokens using generative pre-training, so just a language model. Then you build another language model that is conditioned on semantic tokens. So the generative model is like this. Yeah, sorry, just 2 more minutes. I think this, yeah, couple of more slides, yeah. So the generative model for AudioLM is basically you sample, let's call it S semantic tokens from some density over semantic tokens, right? And then you model C1. Let me explain what C1 is. From some conditional density, which is C1 given S, right? And then you sample C2 from C2 given C1. So this is a hierarchical generative model, right? So these densities, I think you can guess these are all densities over discrete sequences. These are all language models, right? So first you build this language model, just extract semantic tokens from your speech database, build a language model, a GPT, whatever. Then the coarse tokens are actually, as I said, like it's extracted from residual vector quantization, right? So for each incoming vector, there are actually multiple codes depending on how many layers you have. So, in SoundStream, there are 4 layers, so they have 4 tokens per incoming vector. And there are like many incoming vectors depending on what the sampling rate of this encoder is, right? And there's a waveform here. So modeling this with autoregressive modeling is pretty difficult, right? So how would you model this sequence with like GPT, for example? If you want to do full autoregressive training, you would have to flatten this sequence, right? So let's say the incoming sequence is n length. Then if you flatten this, it will be 4n, right? And then you send it to a transformer. I think the complexity can increase quite a lot, right? So what they do is divide these tokens into two. First 2 quantization layers and the next 2 quantization layers, and they model them independently just to manage the complexity of modeling, right? I hope this is clear. So this is like coarse acoustic tokens from layer 1 to Q prime, and then from Q prime to whatever, how many quantization layers you have. So yeah, please ask questions about this if you have any. But is this clear, like how they break this RVQ quantization bottleneck into 2 parts? Because just to manage the complexity of modeling, sequence modeling with transformer. And I hope that the hierarchical generative model is clear. So once you build this hierarchical generative model, then you can use this sampling process to generate audio. So you have C1 and C2, and then you can send the C1 and C2 to the decoder of the SoundStream compression algorithm and generate audio, right? So SoundStream algorithm has a encoder and a decoder and a RVQ bottleneck. Once you have the RVQ tokens, you can send it to the decoder to generate audio, right? So yeah, I see you guys are tired. So I think we can probably, that's it. That's the generative modeling and all the techniques, that go into building a generative model, SSL, compression, and then transformer language modeling on these compressed tokens. So that's one way of building generative model. Other ways, diffusion, which I did not cover. So, but yeah, I think this was enough probably.
Thank you.
First.